Since the dawn of man, there has been an interest in the heavens that so effortlessly bend above us. It has captured the imagination of billions and has left us with countless yet unanswered questions, all of which stir within and amongst us. It very well could be true that that very interest in the heavens and the goal of trying to know it is what led to all of the branches of knowledge today. After all these years of exploration and discoveries of the heavens, what is it that we have come to know about it? The objective metaphysics is existence exists, which implies two corollary axioms, that something exists which one perceives, and that one exists possessing consciousness. Consciousness being the faculty of perceiving that which exists. The axiomatic concepts of objectivism will be sufficient to get us started in understanding reality. This film provides an account of the history of physics, of those explorations and discoveries of the heavens, and does so by following the principles of objectivism, the philosophy created by Ayn Rand. For science and philosophy, we luckily already have some material from natural philosophy and physics, as well as from Leonard Peikoff lectures, which can help us understand the nature of reality in more depth. In a few of Dr. Peikoff's lectures on objectivism, he discussed a humorous epistemological placeholder that he and Ayn Rand would use in place of the question of what existence is made of. They called it the little stuff. The little stuff is that which is where nothing isn't. It fills the universe and can be otherwise called the ether. It is common to hear that the ether was proven to not exist. And in one sense that is true. However, it is also true that there are thousands of ether hypotheses of the last 2,000 years which have been proven to not be true. Specifically, when people talk about the ether being proved false, they are talking about the luminiferous ether. Pop science has taken the idea that the luminiferous ether does not exist to the extreme, turning that statement into no ether exists. This then drips down the pop science tubes until the message becomes, the universe is an empty void where nothingness exists and other universes might exist on the other side of vast stretches of nothingness. These types of ideas about the universe are dead wrong in every regard except one. The luminiferous ether does not exist. That is the only thing that they have correct. Note the repeated use of the word luminiferous in the term luminiferous ether. The luminiferous part of that term is entirely in regard to how light travels through the universe. Quoting Einstein, the man who is said to be the slayer of the ether, we may say that according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable. For in such space, there not only would be no propagation of light, but also no possibility of existence for standards of space and time. This film will explore the discoveries that led to this new ether, the ether that replaced the luminiferous ether. This new ether can be considered to be like the little stuff that is where nothing isn't. As we move through the discoveries that led us to this new form of ether, we are going to hold some objectivist principles in mind, so as to not wander from the purpose of checking our physics and metaphysics against reality. Starting with the axiomatic concepts that existence exists, A is A, consciousness is conscious. And the corollary statement, since things are what they are, since everything that exists possesses a specific identity, nothing in reality can occur causelessly or by chance. Which, for spacing's sake, we will simply write, nothing in reality can occur causelessly or by chance. These principles will be our guide as we go through the history of the ether, They will guide us to the discovery of what the nature of reality is made of, on solid, objective grounds, and will demonstrate that the little stuff fills the ether and that there is nothing prior to it. Part 1. The Crystal Spheres. Like all of our journeys of understanding, we begin at the beginning of philosophy and rational thought. Our questions about what the universe is made from started long before the ancient Greek philosophers. However, it wasn't until the ancient Greek philosophers, like Thales, that the principles of those questions were being bounded by certain rules of logic. Thales was looking for the one in the many. Thales came to the conclusion that all things in the world are made up of water. Thales believed that water was the thing which existed in all other things, and because of the natural changing properties of water, from ice to liquid to gas, that this ability to change was the way in which all things had to change, thanks to the water that they are made up of. Later, the philosopher Heraclitus proposed that the one thing that appears to be common to all things, the one thing in the many, is change. Everything changes, given a long enough timeline. Heraclitus saw this as becoming, and becoming is a process of an object becoming a different object, A ceasing to be A and becoming B. But we didn't substitute A for B. This B is the same A. It's just not A anymore. Because of this, Heraclitus concluded that change necessarily implies a contradiction. But he also concludes that change is the most obvious fact. So it must be the case, therefore, that the most obvious fact of reality is that it is composed of contradictions. Heraclitus, now freely detached from reality, can use whatever he wants to conclude whatever he wants. He chooses to believe that nothingness is a type of somethingness. Nothing is. Everything is becoming. Reality is flux. Heraclitus's philosophy was countered by Parmenides. Parmenides accepted the initial premise Heraclitus presented, that change necessarily implies a contradiction. But Parmenides rejected the conclusion that reality is flux. Parmenides took the position on the opposite side of the change is contradiction coin, claiming that a contradiction cannot exist, therefore change cannot exist, therefore reality is static. Heraclitus had to explain why, if nothing is and everything is becoming, why it appears that things are stationary, solid, unchanging entities. Parmenides had to explain why, if nothing is moving or changing, why does it appear that there are things which are not stationary, not solid, changing entities? Heraclitus answered his question by claiming that the senses are deceptive and that reality can only be known by reason in contradiction to the senses. Parmenides answers his question by claiming that there are no individual entities. The universe is one unchanging entity he calls the One. And since we think we see individual entities, that is evidence that the senses are deceptive. Parmenides' conclusion is false because of the last premise he introduced to his argument. Parmenides' starting basic principle was, what is, and what is not, and what is not can neither be nor be thought about. It is this starting premise that led Parmenides to conclude that Heraclitus was incorrect to claim that contradictions can and do exist. Given this premise, Parmenides then deduced that 1. The universe must be uncreated. The universe has no beginning. And 2. The universe must be indestructible. The universe has no end. If the universe has no beginning and no end, then the universe is eternal. Further, there can be no part of this universe that contains a void, a region of the universe where nothingness is that which is where something isn't. Therefore, 3. The universe is completely full, solidly packed, a plenum. Parmenides' initial premise matches Ayn Rand's objectivist axiomatic concepts. Where Parmenides says what is, Ayn Rand says existence exists, A is A. Ayn Rand's objectivism must also have a solidly packed universe, for the same reasons as Parmenides discovered. There can be no such thing as a thing which is nothingness. There can be no void in the universe. There must exist a little stuff that exists where nothing isn't. There is nothing prior to this little stuff. It is uncreated. It has no beginning and no end. It is eternal. So we will add these discoveries to the list of premises that we cannot contradict as we move forward into learning the nature of the ether. Heraclitus' work had an impact on Plato as well. Plato did not fully agree with Heraclitus or Parmenides, so he formed a new basis for the question about the one in the many. Plato created universals and particulars. Universals are the unchanging perfect forms that particulars are trying to be, but cannot become because particulars are changing and therefore imperfect by this standard. The particulars followed Heraclitus' philosophy, but the universals do not. They are the unchanging nothing which is. To Plato, the particulars are known by the senses, and the universals are known by pure reasoning. Plato concluded his thoughts on the topic by showing that the particulars and the universals are not the same, and that there must exist two different universes or worlds, one for each. According to Plato, the world of universals is real and unknowable by man's senses, and the world of particulars is a fun-house mirror image of the real world, and the senses are only really good as children to remind us of the universals we knew about in the world of universals from where we came prior to our birth. Plato passed these ideas down to his student Aristotle. Aristotle took the names of universal and particular from Plato, but changed just about everything about them. Aristotle believed that all entities are composed of universals and particulars, and that we can mentally separate them from each other, but cannot physically remove them from each other or the entity. No matter without form, and no form without matter. Aristotle also rejected the initial premise of Heraclitus and Parmenides in regard to change. Heraclitus and Parmenides held that change is contradictory, but Aristotle did not believe that change implied a contradiction. Aristotle believed that change was understandable and that change follows from the laws of logic. Aristotle formulated the law of non-contradiction. Nothing can be A and non-A at the same time and in the same respect, as well as the law of the excluded middle. Everything is either A or non-A at a given time and in a given respect. Because of these laws, Aristotle was also able to formulate the idea that change is change from something to something by some means for some end or goal, showing that the world was lawful and orderly because what a thing does depends on the identity of that thing. Because of Aristotle's views on form, matter, and causes, Aristotle had held a teleological view that everything was moving towards its own fulfillment of actualizing its potential. And because of that, it must be the case that motion must always exist, that motion is eternal. Thus, there cannot be a cause of motion which starts motion at a particular point. This chain leads to the creation of Aristotle's prime mover, which is eternal, unmoving, immovable, pure form, pure actuality, immaterial, and perfect. Aristotle suspended this prime mover beyond crystal spheres which move in the heavens. These crystal spheres are intelligent and wish to be as perfect as the prime mover, but they are not pure form like the prime mover, and therefore must move. So they move in the most perfect form of motion, pure circular motion, which revolves around the earth. The crystal spheres love the perfection of the prime mover, and so it is that love makes the world go round. Aristotle, borrowing from Empedocles' elements like fire, earth, air, and water, added a fifth element, quintessence, or the ether, which is what the crystal spheres are made from. Ether is therefore, to Aristotle, a particulate matter, which physically fills the universe. This was one of the first, if not the first, non-theological explanation for the nature of the heavens. But this non-theological approach did not last long, as this ether and the crystal spheres would soon be adopted into Christian theology, making changes to it such that those different layers of spheres became different levels of heaven. Outside the taking of this idea, nothing of value in regard to the ether was produced at this time. Investigations into the nature of the universe would not return for almost 1900 years. Nicholas Copernicus, in 1543, published his work On the Revolutions of the Celestial Spheres, in which he presents an entirely different paradigm of the universe. Copernicus questions the nature of Aristotle and the Church's celestial spheres, suggesting instead that it is the earth that moves. He presents a model where the earth revolves around the sun, and rotates about an axis which is tilted relative to the Earth-Sun orbital axis. Part 2. The Matter-Ether and the Principle of Relativity. Copernicus's new model of the universe provides us with an introduction to the principle of relativity, which will be important for the rest of this series. Relativity means that things can appear differently to different observers. The simplest example is to draw a 6 in the sand while someone else stands directly opposite you and your doodled 6. The other observer will see a 9. They can know that you see a 6 and can understand that they too can see a 6 if they perform a rotation of position. Therefore, we can say that the appearance of the digit is relative to the position from which the observer views the symbol. This is the basic conditions of the principle of relativity. Different people can see different things, even opposite perspectives, but all must agree that the perspective is the same if they make the proper physical changes. Copernicus created a greater example of relative observations. Earth, from a stationary position on the earth, can appear to be stationary itself, while the stars appear to rotate overhead. However, from a position outside of the earth, like from Mars, it would appear that Mars is stationary, and it was the earth that was a wandering heavenly body rotating around Mars. A bug, stationary on a spinning ball, would see you revolving around the ball, whereas you see the ball spinning with a bug clinging to its surface. The motion of objects around you can appear to be moving relative to your stationary position, even if it is you who is moving past the stationary object. This idea that the earth was the one moving was not adopted by others very quickly. One such disbeliever of Copernicus was Tycho Brahe. Brahe was born 3 years after the death of Copernicus. 27 years later, Brahe published his On the New Star, which disagreed with Copernicus that the earth revolved around the sun. He believed that the sun orbited Earth. However, he did believe that the other planets were orbiting the sun. Brahe also disagreed with Aristotle that the heavens were on-changing. as Brahe's work on the new star was about a supernova that Brahe observed in the constellation Cassiopeia on November 11th, 1572, which instantly disproved the idea that anything beyond the moon was eternally unchanging. Most other viewers of the supernova naturally held that it had been some phenomenon somewhere between the Earth and the moon. So Brahe's observation that this was in fact a change in the outer space brought with it another major paradigm shift. Suddenly, every single object that had ever been discovered in the night sky was not now an eternal, unchanging Platonic form, but rather was a physical object with physical properties, and that the light from these objects had to travel from the stars through the ether. Needless to say, this discovery raised far more questions than it answered. Now, there was research jobs for understanding inner space, studying the planets, the sun, other objects in the solar system, and now outer space, studying the stars and the other heavenly bodies that could only just barely be seen. In 1609, Johannes Kepler published his first 2 laws of planetary motion, which knocked down another pillar of Aristotle's celestial spheres. Aristotle believed that the planets moved in perfect spheres, but Kepler's observations of the planet Mars led him to the inductive conclusion that all planets have elliptical orbits. This inductive step requires an understanding of geometry, but once one sees the geometry, one will see why it gives Kepler's first law its 2 results. 1. All planets orbit on ellipses, and 2. The Sun is not located at the center, but at one of the 2 focal points of the ellipse. A year later, in 1610, Galileo Galilei observed the moons of Jupiter. These heavenly bodies were previously observed, but assumed to be fixed stars near Jupiter, trapped in the crystal ether celestial sphere. Galileo observed that these objects were orbiting Jupiter, eclipsing the planet, then eventually moving behind the planet, then re-emerging and eclipsing it again. Today we call these moons the Galilean moons, and they were given the names Io, Europa, Ganymede, and Callisto. Today, however, we know that Jupiter has far more moons than that, having 79 moons in total. This was strike 3 for Aristotle, and it led Galileo to question whether other ideas of Aristotle were incorrect, like whether the speed of light was instantaneous, or if it had to travel the ether, taking time to get from one place to another. Despite the shown issues with the Aristotelian model, people struggled to grasp how it could be possible for Earth to be in motion. If Earth was in motion, that might help explain the apparent motion of the stars, but if Earth was in motion, and the distance to the Sun was great, then the Earth had to be moving at great speeds. And if the Earth is moving at great speeds, wouldn't it be the case that jumping straight up into the air should displace you the distance the Earth moved while you were not touching it? Galileo wanted to put an end to this argument, and in 1632 he published the work that would get him in trouble with the Pope, Dialogue Concerning the 2 Chief World Systems. This dialogue between Salvati, Segredo, and Simplico was used to demonstrate the Copernican model in full, including answering concerns that the fool Simplico asked. Given that the Pope's views match those of Simplico is one of the reasons that the Church had Galileo put on house arrest. Galileo stated openly in the starting section of his book, "I have taken the Copernican side in the discourse." The dialogues thus present the mathematics and theory behind how the Earth moves and the effects that this cause has on the planet, such as the tides. This book contains within it a thought experiment which Galileo may have actually performed. Galileo's thought experiment placed insects, fish in barrels, dripping water, object tossing, jumping men, and burning candles inside the cabins below the deck of a ship with the windows closed. From inside the ship, on a calm day without external forces acting on the ship, meaning no wind or waves are pushing the ship, it is floating still. The insects fly in every direction, no direction appearing to take any more effort than any other direction. The fish all swim in different directions, without any direction requiring more effort than any other. Water from a container with a slightly open valve drips water straight down into the center of a bowl below it. Objects that are tossed with the same required effort, no matter which direction they are thrown. Jumping straight into the air does not cause you to land in a different location than the spot you had jumped from. And the candle smoke rises in each direction equally, not one direction being more favored than another. If you repeat all of these tests when the ship is sailing at an unchanging velocity, meaning the ship will not accelerate or slow down at any time in its movement, each result will be the same as when the ship was not in motion at all. Galileo concluded, the cause of all these correspondences of effects is the fact that the ship's motion is common to all things contained in it, and to the air also. Galileo concluded then that one inside a closed cabin in a ship cannot tell if the ship is moving at a constant velocity or not moving at all. From this, Galileo concluded that if the Earth is rotating on an axis at a constant velocity, the people of the Earth would not notice, as it is equivalent to not rotating at all. All this is explained with what is called Galilean relativity. Galilean relativity can be mathematically formulated with what is called a Galilean transformation. A Galilean transformation is used to move between two frames of reference mathematically, which only differ by a constant relative motion. An example would be that from the point of view of an observer on shore watching the ship sail past, the observer can see a cannonball that is dropped from the crow's nest will move with the same speed as the ship as it falls. So from the point of view of a person standing still on the shore, the cannonball falls with a curved path. To the crew member dropping the ball from the crow's nest, the ball's forward motion is masked by the ship's motion, and the ball appears to fall straight down. Galileo thus presents us with the idea that two observers in different initial reference frames will agree to the time it takes for the ball to fall to the deck of the ship, and will agree as to where the ball landed, but they must disagree on the path of the ball as it appears to them. To one, it is an irreducible fact that they observe the ball falling down while traveling in a positive x direction, while the other must argue that it is irreducible to them that the ball did not make a positive x direction movement, but rather fell straight down. If you flip this example, and the ship's crew member watches the man on shore drop a ball from a high height, the sailor would see the man moving at a steady velocity in the negative x direction, and he would see the ball fall downward in a negative x direction. The man on the shore would only see the ball fall straight down. This is the principle of relativity. The principle of relativity allows us to assume the equations describing the laws of physics have the same form in all admissible frames of reference. Or otherwise stated, the laws of nature must look the same to one observer as they do to another, and their math ought to work out the same. It is essentially this principle of relativity that allows for all science to be possible, as without this principle we would not be able to assume that experiments done in this laboratory will be valid in the laboratory across the world or across the street. So let us add this principle to our current list of principles. The laws of physics must look the same to one observer as they do to another, meaning there is no physical way to differentiate a body moving at a constant velocity and an immobile body. The principle of relativity does not violate the other principles. The idea that the laws of nature do not change from one place to another works hand in hand with the principles that the universe is solidly packed and causally linked. If the principle of relativity was not valid, and was in fact totally incorrect, then that would mean there could be places in the universe that act differently, such as a case where you are observing from shore a man who is on a ship which is traveling at 45 meters per second. The man, standing at the stern of the ship, throws a ball towards the bow of the ship. From these crew members' perspective, the ball traveled at a speed of 13 meters per second. If the principle of relativity were wrong, then you, standing on the stationary shore, would never see the ball reach the front of the ship. The crew member would say it took 3.5 seconds to get halfway and about 7 seconds to travel the full 100 meters of the ship. But from your point of view, the ball would never have reached the front of the ship, but instead would have looked as if the ball was thrown backwards 32 meters after the first second. The only way for this to be possible would be that cause and effect was not the nature of the universe, such that it could be 100% factual that to the crew members on the ship, the ball reached the front, and also true to the people on the shore that the ball was thrown backwards. Clearly, this is impossible, and therefore the principle of relativity fits into causality perfectly. Both parties must agree that the ball was thrown to the front of the ship. But for this to be true, the party on the shore must add the speed of the ship to the speed of the ball. In doing so, both parties can agree that the crew member threw the ball at 13 meters per second. The party from shore merely adds the fact that the ball was already traveling at 45 meters per second when it was stationary in the crew member's hand, and therefore the ball was traveling at 58 meters per second towards the bow, which would be the only way for both to agree that they saw the crew member catch said ball. Let us quickly recap these past events into a new perspective that physicists and philosophers following these intellectual giants would have as their new basis. The universe went from an eternally unchanging state of heavenly perfection, untouchable and unknowable to man, to suddenly an eternally changing state of physical change, causality, and decay, which was just currently untouched by man. The stars figuratively fell from heaven down into the place of mortal men, possible of being created in a lab if understood well enough. Light became an entity that took time to travel from place to place, meaning it had to travel through an entity of perfect transparency. The Earth went from motionless to moving at constant velocities, one rotational velocity about an axis through the Earth, and another velocity of rotation around the Sun. Discovering our place in the universe suddenly became a lot harder to understand, as you cannot even know when you are observing a constant velocity or whether you are observing a stationary object while moving at a constant velocity. With that recap in mind, we continue on to the exploration of the universe, keeping in mind now that future research would be needed in understanding 1. What the ether is made of, and whether it moves or not, and 2. What light is made of, and whether it moves or not. Within the same dialogues, Galileo also argued that light need not be instantaneous, but may actually have a finite velocity. But the closest Galileo could get to that velocity was that light had to travel at least 10 times faster than that of sound. However, research in astronomy, light, and natural philosophy were once again interrupted by the actions of the Church. The natural philosopher René Descartes had written in 1629 through to 1633 about the nature of the ether and the solar system. However, it would not be published out of fear of the Church, and that what they had done to Galileo might be done to him. Descartes decided instead to rewrite this work by softening the heliocentric views. This softened version was compiled into a textbook called Principia Philosophiae, which Descartes wanted to have replace the Aristotelian textbooks which were taught at the universities at that time. The original copy eventually was published in 1664 in the book Treatise on the World and Light, or otherwise called The World. In Book 3 of Principia Philosophiae, under the title of The Observable Universe, Descartes states, "The only difference between my position and those of Copernicus and Tycho is that I don't attribute any motion to the earth." Descartes made a few arguments to demonstrate his case. The first being that the fixed stars are just like our sun, and are not fixed to the outer crystal spheres, but rather are the centers of their own planetary systems. Descartes states that each of these systems is filled with a fluid, openly dismissing the idea that the heavens are empty, and the motion of these fluids drag the bodies like planets in it. And the fluid eddies of the planetary system have smaller eddies, which explain the orbits of the moon around the earth and the orbits of the followers of Jupiter, which were discovered by Galileo. Descartes expresses in this book the principle that Newton later takes as his own, and much later becomes known as Newton's first law of motion. Descartes expressed this first law in 1644 by stating that people tend to believe that motion requires actions, and therefore an object in motion requires an external force to continue said motion. But Descartes shows that that belief is caused by our atomized experience of life on a planet with gravity, and that the opposite is actually true. That it takes effort to prevent the body from moving down, including your arms, that the motion is ever present and we apply effort to stop ourselves from collapsing, and that we require effort to continue motion because of friction and gravity, otherwise we would remain in motion. Descartes saw this motion as intrinsic to the functioning of reality, and assumed that each natural element intrinsically moved at different speeds, such that fire element particles were intrinsically fast, and their quickness tore holes in slower objects which we see as burning or disintegrating. Air, earth, and water were naturally slower elements. Descartes held that the earth was trapped in this fluid and was itself at rest. The quick motion of the ether traps the atmosphere to the earth, and the motion of the air trapped the rocks to the ground, as rock is intrinsically stiller motion, and all is carried by the heavenly fluids. Quoting Descartes, "Let us assume that the earth is at rest, having no innate tendency to motion, because we don't see any such propensity. But let's not think that this prevents the earth from being carried along by the currents of the heaven, following the motion of the heaven without itself moving. Compare this with an unanchored ship that isn't driven by the wind or oars, floating motionlessly in the middle of the ocean, though it may be imperceptibly carried along by the ebbs and flows of the great mass of water. In this strict sense, the earth is not moving, nor are the other planets, because they are not transferred from the vicinity of those parts of the heaven which they are in immediate contact, insofar as these parts are considered as being at rest." Part 3. What the heck is light and ether, Anyway, 4 years before the publication of Descartes' The World, the renowned natural philosopher and father of chemistry, Robert Boyle, was conducting experiments with a vacuum chamber and air pump which he invented. Boyle used his air pump to remove air from his vacuum chamber, to which he had placed a bell which could be struck inside the chamber. Boyle discovered that it was the air that allowed for the sound of the bell, as when the air was removed from the chamber, the striking of the bell would not produce a sound. The air can be removed from the chamber, which prevents the bell sound from having a medium to travel through. Therefore, sound requires a medium of air to exist. However, air was not clearly needed for light to travel. As the chamber was made of glass, and the bell was visible inside the chamber after the air was removed. Boyle concluded that light travels through a medium made of particles so much smaller than air that they can penetrate through the glass, unlike air, and therefore cannot be vacuumed out by his air pump. Boyle also experimented with magnetism with his vacuum chamber, placing a compass needle inside, and after evacuating the air from the chamber, a magnet was moved around the glass jar, which caused the compass needle to move. Therefore, light and magnetism, whatever they may be, can travel through solids like glass, but air cannot. So light and magnetism must be smaller than air. In 1665, Dr. Robert Hooke of the Royal Society and student of Robert Boyle published his book Micrographia, which mostly contains observations he made with his invention, the microscope. The book also contains some natural philosophical explanations of what the ether and light may be. Hooke considered light to be of an exceedingly quick but very small vibrative motion, possibly having the vibration perpendicular to the direction of propagation. Hooke's ether was similar to Descartes' in a few ways, and differed drastically in many other ways. Hooke thought if light was leaving stars in particular form, then stars would have to get smaller over time, as the amount of light particles leaving the stars would leave the star with no more fire element particles after a brief period of time. Hooke, being the man that gave us the spring equation, believed that light had to travel through the universe like a bunch of springs attached to each other, such that a motion of light physically traveled through the universe, but the restoring force of the spring would return energy to the source, and therefore would not deplete the stars. Descartes' ether had sent energy through the little stuff, like energy is transferred through tightly aligned billiard balls, such that no object moved, but rather that light energy would just be the tendency to motion, whereas Hooke held that light itself was in motion. Hooke, being the student of Robert Boyle and main assistant to Boyle's experiment, had learned that sound is propagated by the medium of air, and so, like sound, light traveled in straight lines propagated in all directions with longitudinal spring-like motion, an idea that will be picked up by Christian Huygens some 30 years later, when Huygens describes light spreading in all directions in a series of waves in what he calls the luminiferous ether. Descartes provided an explanation of how the planets are forced to move in the direction of the ether vortex, as he believed that the ether, heavens, was composed of fluid matter, which was in motion. Boyle provided an explanation that the ether was composed of matter that must be very small as to penetrate all things, and Hooke provided explanations as to how he believed light was traveling through that ether. In 1676, Ole Romer provided an observation about the velocity of light, such that it was possible for him to predict a planetary event to the minute. Romer was observing the Galilean moons of Jupiter, and discovered that the moon Io had a constant, predictable orbit around Jupiter when watching it throughout the week or month. However, Romer found that when observing that constant velocity over the period of a year, the time it would take to arrive would shift back and forth between too early and too late. Romer realized that since Earth and Jupiter are in different elliptical orbits around the Sun, there would be points when Jupiter and Earth are as far apart as they can get. And there will be times when Jupiter and Earth are at their closest. The further away Jupiter was from the Earth, the longer it would take light reflecting off Io to reach Earth, and the closer Jupiter was to Earth, the quicker light would take to reach Earth. Romer found that light traveled at a velocity equal to about 22 minutes to span Earth's diameter, or about 220,000 kilometers per second, or about 136,701.66 miles per second. During the time period between 1665 and 1672, Isaac Newton was conducting research and teaching about optics. The former royal scientist of optics was Hooke, to whom Newton disagrees with both in the realm of physics and in a more personal way as well. Newton believed that light had to be corpuscular, and that color was based on the size of the particle. Red light being of a greater mass size and speed, blue light being of a smaller mass size and a slower particle. Hooke believed that light was a spring-like pulse, and that color was based on the compression of the spring-like waves, having red light and blue light be a confused white light pulse, red being more compressed at the first and less compressed near the back, blue light less compressed wave, followed by its more compressed part. This battle between Hooke's ideas and Newton's ideas would persist for hundreds of years. Newton argued that in order for light to travel in straight lines, such as when he made a pinhole light to enter his lab through a window curtain, and for light to reflect off of surfaces, light had to be made of particles. He rejected a dense fluid ether, and that light was a wave of the dense fluid medium itself, stating, quote, "A dense fluid can be of no use for explaining the phenomena of nature. The motions of the planets and comets being better explained without it. It serves only to disturb and retard the motions of those great bodies, and make the frame of nature languish. And therefore to make way for the regular and lasting motions of the planets and comets, it's necessary to empty the heavens of all matter, except perhaps some very thin vapors, steams, or effluvia, arising from the atmospheres of the earth, planets, and comets, and from such an exceedingly rare ethereal medium as we described above." Newton also believed that if, according to Hooke, light consisted only in impressions propagated without actual motion, then in order for the sun to propagate light in every direction in an instant or in time, the light would have to bend into shadows as compressions in a fluid cannot propagate in right lines, and will bend and spread behind an obstacle, meaning the far side of Earth would see daylight bend around the planet, and it would light the sky at night. Newton also wrote that the vortex ether of Descartes and others doesn't account for the moons, as many moons around planets orbit against the supposed flow of the ether. Newton had no answer as to what the ether might be, and the only solution he provides in his book Optics is that God is capable of doing things we don't understand. However, what we got from Newton was that light can be described as a particle that is traveling through a medium. Newton's particles of light were based on the size of particles, And so, despite his research on light reflection being quite solid, and being the basis of optics, the corpusculars didn't have as solid of a basis for color and refraction as he had thought. Newton's hypothesis of light was not at all able to explain diffraction or polarization, and for this reason, some of the scientific community preferred Huygens' wave theory of light. Newton had attempted to explain a possible ether theory, but would later abandon it, stating that he did not feel a need to speculate on ether, as his math of the laws of gravity worked just fine without needing to explain the ether. Newton's universe thus sat nearly empty, but being somehow densely packed, but rare enough to not retard the planetary motion. Hence why he abandoned explaining what it could be. Others rejected Newton's universe, as it suggested that things like gravity acted over vast distances without a direct causal link. Gravity is the word Newton coined from the Latin gravitas, meaning weight. This action at a distance problem would prevent a lot of scientists from accepting Newton's theory, as it was considered to be connected with Newton's attempts to bring occult agencies into physics, something Newton was known for. From the Greeks through to the classic natural philosophers like Descartes and Hooke, the ether was the most densely packed thing in the universe, and action at a distance was explained by causal physical collisions throughout the ether. So others saw Newton's action at a distance as impossible, as it would imply that a particle of light is traveling through literal nothingness, which would have only made sense to someone like Heraclitus. One of the scientists that did not believe Newton was the natural philosopher Christian Huygens, who, in 1690, published his book, Treatise on Light. Huygens adopted a more Hooke-like hypothesis of the nature of the universe and light. Huygens assumed that light was just like sound, and that if the ether could be removed, light would vanish too. Huygens held that light was an effect caused by the disturbance of the ether, not a particle traveling through an ether or through nothingness itself. Huygens believed that light, like sound, spread out in spheres, and each ray of the sphere interacts with the medium particle which exists at every point in space, and this elastic billiard ball bumping spawns new spheres of elastic billiard ball bumping at those points in space, called wavelets. Light then is the effect of the elastic collisions of the ether. Another quick recap. Descartes said that space is filled with matter, which is vortexing around stars. He also stated in his theories on the nature of light that it was instantaneous, as is like being poked by a stick. Ether moves, light doesn't. Boyle said that the ether is filled with a subtle matter that explains both the lack of a vacuum and mechanical interactions like magnetism, and possibly other forces like gravity. Ether is stationary, light travels through the ether. Hooke, Boyle's student and assistant, said that the mechanical ether interaction may be like longitudinal spring-like waves, having gravity and other phenomena like light emitting in all directions from the source through the ether. Ether doesn't move, light is like a spring pulse. Newton originally believed that the ether was stationary, and that the density of it got denser near a planet and rarer the further from the planet. But he changed his mind when he considered that the ether would still slow the motions of the planets, and that it may be possible that the ether is immaterial, a decision he left for his readers to decide. Ether unknown or doesn't exist. Light moves as a particle. Huygens had a different form of vortex theory, similar to Descartes in the sense that the vortex threw lighter matter to the edge, and gravity is the effect of the heavier matter being squeezed by the vortex. Huygens' change to the vortex theory was that light was the effect of a wave propagating through the ether. The Cartesian and Huygens theory can be said to be a vortex theory. Boyle and Hooke have a stationary ether, and Newton, Though stating that not having an ether is absurd, his math didn't need one and spawned a purely mechanical motion of planets. Every form of wave theory or corpuscular debunking of wave theory was assumed that the waves were longitudinal waves like that of sound. In 1725, James Bradley conducted an experiment that was attempted by two other scientists on different occasions. The experiment was to measure the parallax of a fixed star in order to prove the Copernican model. The first attempt was done by Hooke, but Hooke's telescope did not have enough power to properly observe parallax. Hooke, however, left instructions in the failed experiment's paper, which could be followed to construct a telescope of sufficient power. The second attempt was conducted by Bradley's friend Samuel Molyneux, with Bradley helping him. However, Molyneux unfortunately died, and so in honor of his dear friend, Bradley made the third attempt at the experiment. All three men chose the same star, Gamma Draconis, the head of the Dragon constellation. The star was chosen for the reason that it never sets in England, the country of its measurement, and it passes directly overhead at some point of the day or night. Molyneux's telescope was built to Hooke's description, but Bradley had to have a smaller one constructed after Molyneux died in order to fit it into his observatory. The experiment was to detect stellar parallax, which is an apparent change in the position of a star due to the relative position of the Earth as it orbits the Sun. Bradley expected to find he would have to move his telescope in a circle as Earth circled the Sun, as that motion would make it look like the star is moving in a small circle. What Bradley found, however, was that he would have to move the telescope only half of the year. For one part of the year, the telescope had to be pointing slightly in one direction, hitting a maximum of 20 arcseconds. Then it would return back to 0 arcseconds 4 months later. Then, 4 months later again, he needed to move the telescope to a maximum of 20 arcseconds in the opposite direction. And again, 4 months later, it returned back to 0. And then 4 more, and back to the 20 arcseconds in the first direction. This observations of Bradley's was given a new term, called stellar aberration. And Bradley explained it with a simple analogy. If rain is falling straight down, a man standing still in the rain would see it fall straight down. And if the man jumps straight up and down, he will still see the rain fall straight down. But if the man walks perpendicular to the falling rain, he will have to tilt his umbrella in the direction of his motion, in order to stay dry. This is caused by the same Galilean effect as dropping a cannonball from the mast. If the raindrop is 10 feet away when it is at eye level, and is at 0 feet away when it is at foot level, then it appears that the raindrop has moved towards you at a slope. You don't have to worry so much about the rain that is currently above your head, as it will be behind you before it can hit you. This also means that it is the velocity of the observer that causes this apparent position of the star, not the observer's position, which would have been parallax. In September, the Earth is moving at its most perpendicular to the parallel light rays of Gamma Draconis to the north, and the telescope needs to be tilted a tiny amount towards the north. To get an idea of the small amount of tilt, here is a 20 arcsecond difference, and here is a degree difference. In December, Bradley's zenith is moving towards the star and is parallel with the light rays, and therefore the telescope can see the star at 0 arcseconds from zenith. In March, the Earth is moving perpendicular, in the opposite direction it was from September, and the telescope needs to be tilted in the opposite direction from the September measurements. In June, the Earth is moving away, in parallel with the light rays, and the telescope can again see the star at 0 arcseconds. Bradley explained the results of his experiments with the corpuscular theory of light, as the light was acting similar to raindrops falling. Using this idea, Bradley, in 1728, was able to make speed of light measurements, which were relatively close to the ones we know today. But more than that, Bradley discovered that the speed of light was a constant, as light from every star arrived at the same velocity. It may not seem like it today, but this discovery had profound implications. The idea that the speed of light didn't appear to change meant that the ether is stationary in the Earth's frame of reference, which is strange as the Earth is always changing directions as it orbits the Sun. The effects of aberration will not be explained for another 200 years, and all those years are spent trying to explain how to fit stellar aberration into the other theories. Newtonian mechanics of planetary motion, however, was starting to demonstrate that Newtonian mechanics was not a totally accurate understanding of the universe. Just as today we know that Einstein's general theory of relativity must not be the whole picture, as it does not fit perfectly with quantum mechanics. And so too did the physicists of the 18th century come to realize that Newton's mechanics were great for small and close everyday equations, but they could not accurately explain planetary motion in what is famously called the three-body problem. Systems like the Sun, Earth, and Moon were not calculatable with Newton's mechanics, and attempts to use them provided the wrong answers. One of the scientists working on this problem was the prolific mathematician Leonhard Euler, who, in the years between 1744 and 1746, became an anti-Newtonian theorist, because of his work trying to use Newtonian mechanics. Euler eventually returned to the Cartesian vortex theory of the ether. However, the vortex theory predicted the motions of the planets would speed up, whereas the stationary ether theory predicted, as Newton suggested, that they would slow down the motions of the planet, and Euler had found that the Earth appeared to have lost a day since Ptolemy's observations of the changing length of a year. Euler also flipped Newton's ether idea, stating that the ether may be denser in space and rarer near the Earth and other bodies, making gravity an effect where we are pushed into the Earth as opposed to pulled or attracted into the planet. Euler never found a solution to what the ether was. However, his research into waves helped support his belief that gravity and other phenomena are caused by an impulse, as suggested by Hooke. Euler also took on Newton's optics, researching light and color, discovering that things like diffraction were better explained by light as a wave. Scientists like Augustin Jean Fresnel and George Stokes proposed alternative solutions to the reason why the speed of light did not seem to be affected by the ether. They assumed that there existed some form of ether drag, where the ether is dragged by the friction of the Earth when it is near the Earth, and has less or no drag in deep space. To understand this, let us return to the umbrella analogy. If the rain is falling straight down, and you are walking perpendicular to the falling rain, the rain would appear to be falling towards you at an angle. The ether dragging hypothesis would be analogous to the idea that as you walk, the air around you is dragged around you, such that when the rain gets close to you, it gets trapped in your local ether and is pushed by your ether wind. This explanation covers why Bradley may have had to tilt his telescope. If the ether is stationary and doesn't ever move, then the motion of the Earth should cause relativity effects, making the light appear to move at an angle as you move perpendicular to it, and straight down as you move parallel to it. However, this at all does not explain how the speed of light appeared to be constant. Thomas Young, in 1804, was one of the scientists that reasoned that light was a wave, and not a corpuscular as Bradley believed, and that the ether was immobile in the frame of reference of the Sun, and that the Earth had no effect on the ether. But he could not explain the aberration effect. However, Young was able to show that light is a wave in other experiments. His most famous experiment was the double-slit experiment. If light was a wave like sound or water as they expected, then there ought to be an interference pattern when light moves past and through an object in its path. In the same way that a water wavefront hitting a double slit will cause there to be two circular wavefronts, so should light if it is a wave. Young demonstrated in 1803 that by shining a light through the double slit, there was in fact an interference pattern at the screen. Young also knew that light had to be a wave in order to explain why light reflects and refracts at the same time. If light was a single ball, then it could not do both at once. However, Newton had already demonstrated that the ether, which is what would be waving, cannot be doing so longitudinally, as this would cause the disturbance of the motions of the planets and would cause lighting effects that we do not observe. So it was, at the turn of the 19th century, that light had to be a wave. That wave had to be a wave in something, and that something cannot be a wave like sound. Also, light would have to behave like a particle sometimes. The ether would have to have been densely packed, but rare, transparent, fluid, but sometimes solid, frictionless, and also maybe having ether friction drag. The particle theorists at this time attacked Young in his inability to mathematically describe the interference pattern of the waves of light. They thought that they could explain diffraction with the idea that beads of light bounce off of each other and cancel. The particle theorists thought that they could finally kill the wave theory of light by holding a science contest on diffraction in 1818 at the Academy of Science. The winner of this contest would thus put an end to one of the two theories. Either the particle theory or the wave theory was going to emerge the sole victor. The winner of this contest was Augustin Jean Fresnel, whose paper supported the wave theory of light. Fresnel, without knowing much or anything at all about Huygens and Young, had already integrated their two theories into his own original work. Young, discovering Fresnel, suggested that Fresnel submit his paper to the Academy. Fresnel's idea could explain reflection, refraction, diffraction, and polarization, covering all of the topics that had been fought over for the last 200 years or more. One of the judges of the contest, Simon Denis Poisson, who was a particle theorist, thought that Fresnel's paper had a big issue. That being that the center of a circular shadow would have to have a constructive interference pattern, thus having a bright light spot in the center of a shadow, which he thought was ridiculous. One of the other judges and the head of the committee, Dominique Francois Jean Argot, took up the challenge on behalf of Fresnel and proved that the bright light spot does in fact exist as Poisson predicted. This was the end of the particle theory of light. The only thing that was an issue for the wave theory in the past was the longitudinal nature of the waves, but Fresnel ended that issue by proving that light is a transverse wave, not a longitudinal wave. This had a whole new effect on the theory of ether, as transverse waves cannot travel in fluids, but only in solids. It seems then at odds that the ether had to be a solid to allow light to travel, and yet it had to be a solid that doesn't affect the motions of planetary bodies, therefore returning us back to the issue of ether drag. Fresnel in 1830 came up with the math that would be used for predicting and measuring the ether drag by massive objects. For the next 50 years, the scientists battled it out over whether ether drag was occurring or not. In 1851, Armand Fizeau conducted an experiment with the first interferometer. He believed that the light will be dragged around by a medium, and so he uses columns of water flowing in different directions. Fizeau believed that his experiment demonstrated a partial ether drag, but his results were a lot lower than he had expected. A follow-up experiment by Hoek demonstrated that there was no dragging effect, and Hoek could not figure out why his version of Fizeau's experiment failed. In 1871, George Airy conducts an experiment as laid out by Young in 1804, using stellar aberration and a water-filled telescope. Airy concludes that the stellar aberration remains and the ether drag could not be measured. In 1881 and 1887, Michelson, and later Michelson and his partner Morley, conduct the most famous ether dragging experiment, the Michelson-Morley interferometer experiment. The Michelson-Morley interferometer experiment found that light appears to move through the ether at the same velocity in every direction, no matter where the Earth is in its orbit, and no matter which way they rotated the experimental apparatus. This is where the conclusion that the ether doesn't exist comes from. But this experiment cannot disprove an ether, something that has to occupy space. This experiment merely showed that the ether was not being dragged. It proves that the luminiferous ether doesn't exist. That light doesn't need a material substance called a medium, like air, water, or glass, in order to travel. It proves that the little stuff which exists where nothing isn't is not a particulate matter. From this experiment, alongside Bradley's and Airy's experiments, we can add to our list of premises which cannot be contradicted. The ether is not a particulate matter. Light traveling through this non-particulate ether retains a constant velocity in all directions to all observers. Part 4. The ether is dead. Long live the ether. During this time between 1799 and 1887, scientists in different fields of physics were hard at work on electricity and magnetism. The invention of the Voltaic pile in 1799, the first electric battery, allowed for the first time ever a steady continuous stream of electrical charge, which was thought to be a kind of fluid that flowed through the wire like water flows inside of a hollow tube. Before this continuous flow of electric fluid, it was demonstrated that static electricity can be used to reduce chemicals like tin, zinc, and antimony from their salts, which was something that was already known by alchemists, that fire will cause the transformation of matter in a process called calcination. The first productive use of this continuous flow of electrical fluid was used in chemistry experiments to reduce chemical compounds into their elements, as it was discovered by William Nicholson and Anthony Carlisle in May 1800 when their Voltaic pile's 2 wires were placed in water. The water completed the circuit of the battery, and the 2 ends of the wire produced bubbles, which turned out to be the gases of oxygen and hydrogen. This discovery led scientists like Sir Humphrey Davy to use the Voltaic pile to conduct chemical experiments, such as isolating, for the first time, chemical elements of calcium, strontium, barium, magnesium, and boron, as well as using the piles to create an arc lamp, the first incandescent light, which, despite our taking for granted view of light bulbs, was a huge deal, as this showed that there was some connection between electricity and light. That electrical sparks produced light sufficient enough to light a room. April 21st, 1820, Hans Christian Ørsted found that a magnetic compass needle was moved in the presence of the electric current, which was supplied by the Voltaic pile. Ørsted had no clue what was occurring, simply that it was doing so in spiral circles around the wire, and also that they were in planes perpendicular to the wire. The effect strength depended both on how close to the wire it got and the magnitude of the current. That reversing the current reversed the compass needles, and that it penetrated all non-magnetic bodies, whereas it moved all magnetic bodies due to their resistance of the electrical conflict. This was the first connection between the 2 natural phenomena, and its publication caused an explosion of scientific discoveries. In fact, it is likely one of the most important discoveries in human history. Within weeks, André-Marie Ampère had already developed Ørsted's discovery into a mathematical formulation on electrical and magnetic interaction, and later formed Ampère's force law, which describes the production of mechanical force by the interaction between the electrical current and the magnetic effect related to it. This inspired Humphrey Davy and William Wollaston to attempt to use the electric current and the magnetic effect to create a mechanical action, otherwise called an electrical motor. But the pair failed due to the fact that they thought the circular magnetic effects were spiraling along the wire. Davy's student, Michael Faraday, in 1821, picking up the pieces of his supervisors, discovered that the circular effect was not spiraling up the wire, but rather that it was more like a set of enclosed cylinders around the wire, which allowed him to create the first electrical motor. In fact, he created two. In 1825, British electrical engineer William Sturgeon invents the electromagnet, a horseshoe-shaped bar of iron with a loosely wrapped coil of copper around it. When a current was run through the copper coil, the magnetic effect of the currents were somehow given to the iron bar, such that the bar, when the current is flowing, becomes a super strong magnet, and stops when the current stops. Faraday, in the summer of 1831, used this electromagnetic idea of coiling wires around iron, and wrapped a wire around one side of an iron ring, and another wire to the opposite side of the iron ring. One wire was connected to a battery, the other to a galvanometer. Faraday discovered that the galvanometer's arm would move briefly when the current was turned on or when the current was turned off. The current had induced a current in the second coil. To Faraday, this meant that there was some sort of tension in the state. To better understand what was happening, Faraday experimented with a permanent magnet instead of an electromagnet, and found that he could move the needle like that of the last experiment by moving the permanent magnet in and out of the coil of wire. The motion of the magnet past the coil caused or induced a current in the wire. Faraday knew that magnetic forces could be seen with the use of iron filings, and he used this visual of the lines of force to show the law that the magnitude of the current is dependent upon the number of lines of force that pass through the conductor in a unit of time. Faraday then quickly followed that discovery with the idea that a continuous stream of electric current can be produced by the spinning of a copper disc between the poles of a powerful magnet. This dynamo was the first design of the electric motor that we use for just about everything every day. Faraday, being of a lower class and having gained all his learning from books he binded as a bookbinder, was either unwilling or put down for his speculative ideas, and did not tend to share them with other scientists, except for his supervisor Davies and a few others. However, on April 11th, 1846, a colleague of Faraday's was to give a lecture at the Royal Institute in London. But he had terrible stage fright, and at the last moment panicked and ran out into the streets, leaving Faraday to cover him. Unprepared, Faraday briefly discussed his speculative theory of the lines of force. These speculations caused a great stir in the community, but as Faraday did not have the mathematical skills to back up his claims, most people did not follow through with his speculations. Faraday had received a request to convey his speculations by a one Richard Phillips, Esquire. The letter Faraday wrote to Mr. Phillips was titled, Thoughts on Ray Vibrations. In this endeavor to explain himself, Faraday writes, quote, The point intended to be set forth for the consideration of the hearers was, whether it was not possible that the vibrations which in a certain theory are assumed to account for the radiation and radiant phenomena may not occur in lines of force, which connect particles and, consequently, masses of matter together, a notion which, as far as it is admitted, will displace with the ether which, in another view, is supposed to be the medium in which these vibrations take place. Perhaps I am in error in thinking the idea generally formed of the ether is that its nuclei are almost infinitely small, and that such force as it has, namely its elasticity, is almost infinitely intense. But if such be the received notion, then what is left in the ether but force, or centers of forces? As gravitation and solidity do not belong to it, perhaps many may admit this conclusion. But what are gravitation and solidity? Certainly not the weight and contact of the abstract nuclei. The one is the consequence of the attractive force, which can act at distances as great as the mind of man can estimate or conceive, and the other is the consequence of the repulsive force, which forbids forever the contact or touch of any two nuclei. So that these powers or properties should not in any degree lead those persons who conceive of the ether as a thing consisting of force only, to think any otherwise of ponderable matter, except that it has more and other forces associated with it than the ether has. It may be asked, what lines of force are there in nature which are fitted to convey such an action and supply for the vibrating theory the place of the ether? I do not pretend to answer this question with any confidence. All I can say is that I do not perceive in any part of space, whether to use the common phrase, vacant or filled with matter, anything but forces and the lines in which they are exerted. The lines of weight or gravitating force are certainly extensive enough to answer in this respect any demand made upon them by radiant phenomena. And so probably are lines of magnetic forces. And then who can forget that Monsanti has shown that gravitation, agration, electric force, and electrochemical action may all have one common connection or origin, and so, in their actions at a distance, may have in common that infinite scope which some of these actions are known to possess. The ether is assumed as pervading all bodies as well as space. In this view now set forth, it is the forces of the atomic centers which pervade and make all bodies, and also penetrate all space. As regards space, the difference is that the ether presents successful parts of centers of action, and the present supposition only lines of action. As regards matter, the difference is that the ether lies between the particles, and so carries on the vibrations, whilst as respects the supposition, it is by the lines of force between the centers of the particles that the vibration is continued. As to the difference in intensity of action within matter under the two views, I suppose it will be very difficult to draw any conclusion. For when we take the simplest state of common matter, and that which most nearly causes it to approximate to the conditions of the ether, namely the state of the rare gas, how soon do we find in its elasticity and the mutual repulsions of its particles a departure from the law, that the action is inversely as the square of the distance. In 1849, William Thomas, commonly known as Lord Kelvin, in a letter to Faraday, explained mathematically how Faraday's predicted magnetic fields should affect the plane of polarized light. This led Faraday to reattempt his old experiments, and was able to prove that magnetism and light are related, in what has come to be known as the Faraday effect, which in simple terms demonstrates that a magnetic field can be used to rotate a polarized light, or, even more simply put, a magnetic field can control light. In 1852, Faraday wrote a paper entitled On the Physical Characteristic of the Lines of Magnetic Force, in which he cautiously shares his speculative philosophy on what he called force lines, and their role in the process of action at a distance. The scientists and philosophers of the last 2,000 years were attempting to get rid of this action at a distance, using the ether as some sort of mechanism, which was getting more and more complex. By this time, Faraday had held an entirely different view of that ether, no longer believing, like the others, that it was composed of particulate matter, but rather that the ether was the field which was capable of supporting the tension of electricity and magnetism's lines of force. The work of Faraday led to the work of James Clerk Maxwell. 14 years before the famous Michelson-Morley experiment conclusion, in 1873, James Clerk Maxwell had just completed his treatise on electricity and magnetism. Maxwell's treatise refrained from making claims about the ether, stating within, quote, "These and many other phenomena of electrical discharge are exceedingly important, and when they are better understood, they will probably throw great light on the nature of electricity as well as the nature of gases and of the medium pervading space. At present, however, they must be considered outside the domain of the mathematical theory of electricity." Maxwell, like Faraday and Newton before him, did not want to lose the facts of reality to speculations on the ether, and therefore none of them came to anything but physical truths to construct their mathematical formulations. All of Maxwell's equations are derived from physical observations, and the equations explain how the fields of force are constructed as demonstrated by the physical experiments that defined them. The addition of the Lorentz force law completed the understanding, as the force law explains how these fields will affect the things within them. Maxwell therefore showed how objects in the field create forces, and how those forces would in turn affect the objects in the field. Let us get a better idea of what a field is. A field is an abstract idea that says there can be assigned a value for each point in space and time. This value represents some physical quantity. For example, we can take a room and divide it up into imaginary boxes of equal volume. Say each box is 1 cubic foot, meaning extends 1 foot east to west, extends 1 foot north to west, and extends 1 foot ground to ceiling. If the room is 1,000 cubic feet, 10 feet in each direction, then there are 1,000 imaginary boxes stacked 10 by 10 by 10. This room can be said to become a field when we put a thermometer inside every box. The field in this case would be a scalar temperature field. The values at each point in the space of the room would be the temperature at that specific location, and those temperature readings would change over time. We can also stick other measuring devices in each box, like a gravity detector, an electromagnetic detector, a photon detector, a wind speed detector, and so on. Each of these detectors would register some physical quantity, which is the result of having received energy from the environment. The field of forces of gravity would have vectors which point in the direction of the Earth. The electromagnetic detector would register some electric and magnetic fields of force, etc. The fields, then, are just our way of dividing up space and time so that we can understand what each point in space and time is experiencing at any given moment. Faraday's lines of force require time to propagate, and Maxwell helps explain this with a real example. An electric current can cause a magnetic field to appear, but it doesn't have to be an electric current. A time-varying electric field, a short vibration in the electric field, can also cause a time-varying magnetic field, a short vibration in the magnetic field. And a time-varying magnetic field can cause a time-varying electric field. And this self-propagating electromagnetic field can be written as a wave equation, and the speed of this wave happens to be the same as the speed of light. Leading to the conclusion, quote, "The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. From this, we can conclude that light is an electromagnetic energy disturbance in the electromagnetic field." Conclusion: that which exists where nothing isn't. The little stuff is that which is where nothing isn't. It fills the universe and can be otherwise called the ether. The ether, if it had the ability to do so, might wish to quote Mark Twain to say, "The reports of my death have been greatly exaggerated. The ether is alive and well despite the claims to the contrary." Today, that ether has taken on the name fields or even space-time. The little stuff is not particulate, but that was never a requirement for Ayn Rand or Leonard Peikoff. All that was philosophically necessary was that something exists where nothing isn't. Today, we know that light is a packet of energy, an electromagnetic disturbance in an electromagnetic field, and that its speed is a result of its nature as a massless energy chain reaction of time-varying oscillations in the ether. We have walked through the history of the ether and have come out on the other side having learned that the ether didn't die. The bad ideas about it died, and what was left standing has led to the marvels of the world around us today. The physics of field theory, which has grown from this discovery of this new ether, has advanced science and technology tenfold, if not more, much, much more. Refresher on the principle of relativity. Galileo, using one of the fastest means of transportation available to him, made a thought experiment about sailing ships and how physics tends to stay the same even if you are on a fast-moving ship. For example, you and your crewmates can play a game of cards inside the cabin of a ship while you sail at its top velocity. And the cards remain on the table, omitting any sloshing. However, to people that can see you playing cards from the shore, the cards, say as you fold your hand, dropping the cards straight down, appears to move at great speeds from where they used to be to meters away in the direction of the ship's movement. What appears to you as the cards falling straight down appears to people on the shore like you toss them across the sea such that they landed where the table will be, not where the table was. Galileo summated that the laws of physics hold good for objects in constant motion, that the motion is relative, that to the crew on the ship, the people on shore are moving, and those people on shore say the people on the ship are moving, and aliens watching the Earth floating past think that both of you are moving. There is no universal stationary object which all other objects are judged against. There is no center or stationary. Everything is stationary to their own perspective, and everything else appears to be in motion or stationary according to their stationary position. Einstein's special case of the principle of relativity is no different from Galileo's in principle, namely that Einstein's two postulates fall in line with the essential nature of the original principle. The first postulate states, physics is the same for all observers, just as Galileo showed. The second postulate is actually a derivative of the first, being that it states, the speed of light is the same for all observers. The second postulate comes from the first postulate, and from the work of James Bradley and James Clerk Maxwell. Bradley first found that the speed of light was the same no matter what star he measured. No matter which direction the Earth was moving, light was always the same speed. Maxwell showed that the speed at which the electric field interacts with the magnetic field is identical to the speed of light. Einstein, through his work, which we will explore here today, tied the two together and stated that the physics that is the same for everyone is a physics which uses light to interact, and therefore, no matter how fast or motionless you are, if you exist, then light is moving at the same speed as it always is. For physics to be the same on a train, which is moving at its top velocity on Earth, or a lab on Earth, which is spinning and orbiting the Sun, or a lab which is stationary in the Sun's frame of reference, which is orbiting the Milky Way's center, then the speed at which these atoms interact, the speed at which the atoms of brain neurons must interact, must be the same for all observers. For this, Einstein needed to show that 1. Photons are light, and photons interact with material as packets of wave energy. 2. That material which the photon interacts with are made of atoms, that atoms exist. 3. That Maxwell has a Galilean relativity problem, and that problem is solved by understanding what must physically be observed by people outside the moving frame of reference. And 4. That mass and energy are equivalent, which is the consequence of 3. All of which Einstein achieved in 1905 at the age of 27. The first paper was on what is called the photoelectric effect, which establishes that light comes in wave packets called photons, and that the energy of a photon is quantized. Newton, 300 years earlier, showed that light was heating up objects, not just shining light and color. That materials absorb light and reflect color and heat. Einstein showed that the absorption of light at certain frequencies could cause the material to emit electrons. Before Einstein's photoelectric effect experiment, scientists in electromagnetism thought that electrons could be emitted through a continuous buildup of continuous light waves, such that the material would continue to absorb energy until it filled up to a limit and would then emit the electron. The experiment proved that this is not the case. Light of a certain frequency, which is lower than the threshold for the emission of the electron, never emits the electron, no matter how long you wait or the intensity of the light. However, a low-intensity, short burst of light at the correct frequency can emit an electron. Einstein thus showed that the best description of a photon is that it is a discrete packet of energy, a quanta of energy, not a continuous wave through space. This we will come back to when we get into quantum mechanics in later videos. In the second paper, Einstein modeled Robert Brown's pollen in water observations to show that the random motion of the pollen was caused by atomic interactions of water molecules, which at various times, interacting in various ways, interacts with the pollen in different places, in different degrees, and the resulting atomic forces physically move the pollen, resulting in what appears as the pollen randomly walking around the petri dish. The third paper, Einstein showed that Maxwell's equations of electromagnetism was not matching up with Galileo's principle of relativity. To understand this, we need to get a bit more acquainted with Maxwell's equations. The equations known as Maxwell's equations were not created by Maxwell. Maxwell simply compiled a list of experimental equations, and that list was a lot longer and a lot scarier looking than the set we know today. The set we know today was actually provided by Heavyset's simplification of Maxwell's compiled list. Inside 2 of the 4 field equations, Gauss's law and Ampere's law, there can be found 2 constants. The constant inside of Gauss's law is epsilon naught, which is called the permutivity of free space, which is the capability for an electric field to permeate a vacuum. There is also the permeability of free space, which is denoted mu naught, which can be seen appearing in Ampere's law, and is how permeable space is at letting magnetic fields flow through it. The permutivity value can be determined by using Coulomb's law, where the charges of 2 objects are known. The force between them is known, and the distance between the 2 charges is known. I have covered how Coulomb first found the value for the permutivity of free space in the History of Electricity video. We can just say that if 2 balls are given a charge of electricity, then they will exert a force on each other. The strength of the force will depend on the amount of charge and the distance between them. The constant that Coulomb used was necessary because the environment in which the charges interact makes a difference, even in a vacuum tube. The product of the charges, divided by the distance squared between them, is not the exact force. The permittivity is a constant of proportionality between the electric field in a material to the electric displacement in that material. And in this case, the material is the ether, or free space. You can have, as an example, the permittivity of water as well, which is not very permitting at all. If you take two metal plates and you charge one to be negative and the other to be positive, an electric field will form between the plates. If you place water between the plates, the electric field in between will decrease. If you remove the water and air between the plates, all that is left is the little stuff, which we find to have a constant property value of 8.854 times 10 to the negative 12 farads per meter. The permeability value is a proportionality between magnetic induction and a magnetizing force when forming a magnetic field. For example, the permeability of iron is very high and will become magnetic in the presence of a magnetic field, whereas wood has a very low permeability and can ignore the presence of a magnetic field. The wood is not permitting the magnetic field. The iron is permitting the magnetic field. The little stuff of the ether, or free space, has a property of permeability which is equal to about 4 pi times 10 to the negative 7 Henry per meter. Maxwell found that a time-varying electric field acts like a current and applies to Ampere's law, which says that a magnetic field is created. By applying this to Ampere's law, the equation becomes mu naught times epsilon naught times the time-varying electric field. This leads to a wave equation, and wave equations have waves which have velocity, and therefore Maxwell was able to find the speed of the electromagnetic wave, using only these two constants which are experimentally demonstrated. Maxwell found that the electromagnetic wave happens to travel at the same speed that light was being experimentally demonstrated to be, and was therefore able to link electromagnetism with optics, showing that light is in fact an electromagnetic wave. This explains why the tests of the speed of light through an ether demonstrated a constant speed of light, no matter the motion of the observer or the source. The wave speed of light is determined by the properties of the free space, or the ether if you prefer. Here then we can add that the constant velocity of light is the result of the electromagnetic properties of the ether. Maxwell's electrodynamics has a Galilean relativity problem as shown by Albert Einstein in the introduction of his 1905 paper on the electrodynamics of moving bodies. Let us explore this quickly using a simplified electromagnetic law, which states that an electromagnetic force is created by an electric force and/or a magnetic force. If a charged particle is displaced by this force, the displacement must be caused by one or the other, or a combination of the two. An electric force is caused by an electric field interacting with the electric field of the charged particle. A magnetic force is caused by an interaction between the magnetic fields. We know from the History of Electricity Lecture 2 video, a magnetic field will only exist around moving charged particles, and therefore, the current creates a magnetic field, as does the moving test charged particle. A stationary charged particle does not cause a magnetic field, and therefore, a stationary charged particle cannot interact with the current-carrying wire's magnetic field. Einstein used this law to prove that there is a Galilean relativity problem with Maxwell's equations. Paraphrasing Einstein, he writes, "A copper conducting wire has no built-in magnetic attraction. as the wire has an equal number of positive and negative charges, making the wire neutral. Maxwell's first equation, Gauss's law, says that an electric field depends on the charge density. A net charge would mean no electric field, which means no electric force. Even if we hook up a battery and get the electrons flowing, the charge density remains the same, and so there is still no electric field, and therefore no electric force. Maxwell's last equation, called Ampere's law, states that a moving current does create a magnetic field. The Lorentz force law states that an electromagnetic force exists if an electric field exists and/or if a charged particle is moving with a velocity through a magnetic field. We currently do not have an electric field present, but we do have a magnetic field now. But without a charged particle moving through it with its own magnetic field, there will be zero force. Here Einstein points out that the relative motion of the objects in the scene would violate either electromagnetism or Galilean relativity, both of which are experimentally confirmed to exist. So there must be something wrong with our interpretation. If we put a charged particle in motion near a copper wire, from the point of view of the stationary wire, a charged particle's magnetic field is moving through the wire's magnetic field, and, therefore, a force is created. But from the point of view of the charged particle, the wire is moving, and it is stationary, and so there is no velocity of the particle, which means there is no magnetic field for the charged particle, and the wire is neutral, so there is no electric field from the wire, and therefore there is no force whatsoever. From this point of view of an object moving relative to the charged particle, the laws of physics have changed, and Maxwell's equations would need to be rewritten, up until they stopped moving with the charged particle, where they would need to return to the old equations. This would mean that relativity wouldn't hold for objects in motion, which is the only reason for relativity to exist at all. Something is wrong here. When the observer is moving with the charged particle, there is still a force applied to the charge, yet in this frame of reference, there is no force generated by an interaction of magnetic fields as the charge is not moving, meaning the force can only be created from an electric field. The only way for an electric field to exist in this reference frame is if the charge density in the wire was not neutral. The only way to satisfy electrodynamics and the Galilean principle of relativity at the same time is if space and time are relative, as charge is invariant and does not change with respect to motion. This is where the concepts of length contraction and time dilation are implemented into the principle of relativity. The only way to account for the forces affecting the particle would be if the charges in the wire are no longer neutral, such that there is a higher density of particles of one kind or the other in the wire, which will depend on the point of view you observe the experiment. From the perspective of a stationary charged particle in the wire's magnetic field, the density charge would come from an increase in the protons in the wire. Assuming the wire is solidly packed with atoms that cannot move, this effect can only be true if the lengths of the proton have contracted. This would produce a high density of protons in that region, which produces an electric field, which would interact with the electric field of the stationary charged particle, and therefore an electric force interaction would occur. The solution to Maxwell's electrodynamic problem can therefore be solved using a special case of the principle of relativity, which leads us into Einstein's special relativity. To understand Einstein's special relativity, we need to return our minds back to our bodies. We need to be the measuring device, taking in perceptual data or energy from the outside world, pursuing objectivity completely. Simultaneity, time, and position. Perception is based on simultaneous sensory interactions. The formation of the perceptual level is the result of neurons firing together, and therefore wiring together, caused by the energy received by the sense receptors. When a sense receptor receives energy from the external world, it activates, and that is the activation of a biological cell, which has similar physical requirements of the life the entity helps make up, and therefore it must consume energy to function, and then reuptake its source of energy to prevent death and to continue functioning for the next step. The activation of a cell causes the cell to become temporarily unable to activate again, equivalent to not being able to kick because your leg has just kicked and cannot kick again, it is at full extension. The cell takes a moment before it can fire again. When the cell is back to ready mode, it fires again and sends the exact same signal in parallel with all the other cells that fired with it the first time. Given enough exposure to repeating simultaneous activations, patterns emerge in the cortex: dots, lines, circles, squares, triangles, etc., including patterns of motion, for example. The detection of a line in a column of cells, say A, B, C, D. The line was first detected by A and B, but then the column A was off, and B and C were on. Then B was off, and C and D were on. This impressionist-like detection of lines develops into perceptual detection of motion, either the motion of the object or the motion of us as the subject. An essential characteristic of a percept is the fact that it is perceptually constant. It does not vanish into thin air. It keeps its shape, size, color, etc. For an object to be perceived, it needs to be something that remains the same. It doesn't change over many reoccurring activations of sense receptors. And it needs to be occurring simultaneously to every sense receptor receiving energy from it. The perceptual level of cognition is based on simultaneous sense reception activations. This is what allows for classical conditioning in animals. The animal, or a small child, see baby Albert, is exposed to an object, and is constantly simultaneously exposed to that of a different percept, until the animal's perception of that object includes this other, unrelated percept. Say you have a speaker play a sound at the same time the object, a rat, opens its mouth. Even a grown adult put in that situation will be taken aback, wondering how it is that the rat made that noise. It would appear that the rat did make that noise precisely because it happened at the same time, many times, a series of simultaneous events. The formation of percepts comes from things that don't change in space or time, omitting the movement of the object or subject and omitting decay lengths of materials. Implicit in a percept is space and time. That thing over there at this moment, at this snapshot of sense detection. The perceptual observability of causality implicitly starts to provide this, then that. And those causal percepts come from experiencing one set of simultaneous sensory detections following another set of simultaneous sensory detections of an external simultaneous interaction of objects, aka perceptual awareness. When children learn about the science of time measurements, they learn that by measuring the amount of clicks on a clock an event took to go from start to end is how you measure time. Measuring time is an abstraction, an answer to the question, what would my senses simultaneously perceive at this simultaneous click of a clock? The concept of time is tied to the question, what would my senses simultaneously be experiencing if I paused somewhere in the causal chain of events? Time is the product of experiencing causality perceptually, experiencing the external simultaneity of subject-object interactions simultaneously with the internal simultaneities of sense detection and integration. When we view the clock to see the time, the clock needs to be visible, which means light needs to be coming from a light source, reflecting off of the clock and reaching your eyes unimpeded. However, we have learned how and why light takes time to travel. We cannot change that fact of reality. Light moves at a finite speed. So when we look at the clock, what we see is coming at us from the past. The light that immediately strikes our retina the moment we open our eyes to the clock face is light which had already left its source, traveled the space of the room between it and the clock face, reflected off of it, and traveled the space between the clock and your eye. Within a room, and given the speed of light being so quick, the time it takes for you to see the clock face will match the physical mechanisms of the clock, given its human mechanical scale, despite time having changed, and so, typically, you cannot see very far into the past. However, the same cannot be said of objects in space. For instance, from Ole Romer's work, we know that it takes about 8 minutes for the light of the sun to reach Earth in a straight line. So if the sun were to magically vanish, it would take us 8 minutes to notice. The research of this ether that light was traveling through to get from the sun to us led to the scientist James Bradley discovering that light always travels in that ether at the same speed. Further research was then conducted to check whether the Earth's motion, or something about the Earth, was causing it to only appear as if it were traveling at the same speed, through a process they called ether drag. This led to the scientists Michelson and Morley to conclude, through not finding any drag effect, that the ether drag hypothesis, also known as the luminiferous ether theory, was to be rejected. If the effects of the speed of light in vacuum is an illusion, it is not one caused by ether drag. The speed of light as a constant was proven by James Clerk Maxwell by showing that the speed is the speed at which the fields of electricity and magnetism interact. And therefore, nothing can be faster than the causal connections which allow for the existence of all observers. Einstein takes only 2 facts of reality to set up special relativity. 1. The speed of light is the speed of causality. 2. Physics works everywhere, whether you think you are moving or not. These 2 facts, and our fact about the sun's light distance from Earth, helps us set up a great visual of what must be true. The sun is 8 light minutes away from Earth, meaning it takes 8 minutes for light to travel from the sun to Earth. Now imagine a situation where Earth has 2 suns, and it is set perfectly between the 2 suns. We know it is perfectly in between because it takes 8 minutes for light to reach the Earth from both suns. Now imagine that we send 2 rockets off of the planet, one on either side of the planet, complete opposite, aiming towards the 2 suns. Finally, imagine that at some small time t, briefly after the rockets launch off, both suns vanish or explode or dim or brighten or the color changes, whatever, so long as it is a light effect which takes the Earth 8 minutes to notice. Are the events simultaneous to the rockets like they are for the Earth? Very apparently, they cannot be. For the rocket on the left side is closest to the left sun and sees that sun's change in less than 8 minutes, and sees the change in the far sun in more than 8 minutes, and vice versa for the rocket on the right. Therefore, what is simultaneous for the Earth was not simultaneous for the rockets, and therefore, if one's understanding of time is based on simultaneous events occurring with the hands of your clock, then time cannot be universal like Newton held. For time to be universal would require that all 3 observers, everyone on the 2 ships and everyone on Earth, sees both suns vanish, or whatever, at the same time, which would mean that light would have to reach the rockets, which are not in the center, at the same time, and at the same time that the Earth receives both simultaneously. This would mean that light would have to travel very fast for the far rocket, normal speeds for the Earth, and slower for the close rocket. This was the presumed position, which is ether drag, as the scientists thought it had to be the case that all three were experiencing universal time, and so the ether dragging effects of the rockets and the Earth must be speeding and slowing the light to make it appear as if universal time did not exist. After Michelson and Morley smashed the ether drag, the only conclusion left to draw was that what counts as simultaneous events to one person doesn't mean it's simultaneous for others. This brings us back to the solution to the Maxwell-Galileo problem. We said earlier, the only way to satisfy electrodynamics and the Galilean principle of relativity at the same time is if space and time are relative, as charge is invariant and does not change with respect to motion. We now know that velocity of objects must be relative to observers, as this means that different observers see the same events in space at different times. So we get two investigators, and they are placed in different frames of reference. One investigator is riding the wire. The other is riding the charged particle. Both investigators agree that 1. Someone is moving. 2. The particle and the wire move further apart after some time t. 3. Both agree that the speed of light is c. And 4. That physics is working. They are not exploding on-causally. Special relativity. The manner in which to apply these equations, known as the Lorentz transformations, is similar to applying the Galilean transformations. In Galilean relativity, we saw that the speed of a thrown object was added or subtracted from the speed of the object it was thrown from, in order to have our math match reality and conform to each person's point of view. If a man on the shore wanted to know why the sailor thought the ball was only moving at 50 kilometers an hour, he had to remember that the sailor forgot about the relative motion of the ship. So the man on the shore subtracts the ship's motion and gets the same answer as the sailor, and vice versa. Lorentz transformations make clear that the ether is basically a fixed quantum field and light travels through it at the same speed in all directions, and matter which interacts with that light also travels through it, but the light is only attached to the ether, so the motion of the matter does not change the speed of light. Because of this, you apply the Lorentz transformation by remembering that the sailor of the spaceship, which travels at the speed of 0.7 c, forgets about the relative motion of the ship. And so the man on the planet has to multiply the sailor's measurements of time and distance by a factor which keeps the speed of light constant. This provides us with the definitions of proper time and proper length. Proper time: the time that elapses in the frame in which events all occur at the same location. Proper length: the length of an object in the frame in which events all occur at the same time. Alice and Bob are our two investigators. Alice stands on a train platform, holding an extended rod affixed to a flashbulb in each hand, which she is extending a total of 2 meters apart, in an east-west direction. Alice, using her brain, fires a neuron signal which is to have both hands turn on the flashbulbs at the same time. The light which is emitted from the flashbulbs will reach Alice's eyes at the same time. As light must always travel at the same speed in the same medium, then the flashbulbs must be equally far apart from her eyes, and the lights, from Alice's perspective, can be said to be emitted simultaneously. Bob is on a moving train, adjacent to the platform. Bob is moving at 0.7 c, eastward relative to Alice. If Alice is seeing both lights at the same time, then before Bob can see Alice at all, as the lights have not yet reached Bob, he uses his smarts and does the math. Since the speed of light is c always, since Alice has the two flashbulbs 2 meters apart, since Alice appears to be moving at negative v, then the light moving negative c must take longer to reach the left side of the platform than the light moving plus c reaches the right side of the platform. Therefore, if Bob believes Alice when she reports that she saw both lights, requires for Bob that the lights were turned on at different times. Bob would find Alice had to have turned on the east light first, then much later turned on the west light. Bob checks their math. According to Alice, the two light bulbs are 2 meters apart and they reach her at a time difference of 0. So Bob plugs this into the formula. The difference in time between the lights turning on for Bob is equal to gamma times the velocity of the train divided by the speed of light squared times 2 meters plus 0. Since Alice is moving, according to Bob, at negative 0.7 c, Bob finds a time difference of light flashes must have been 6 nanoseconds apart. Bob takes the flashbulbs and they repeat the experiment. Bob now sees the light reach him at the same time. So what will Alice find when she checks her math and diagram? When Alice has the lights, she reports that the lights reach her at the same time, 0 nanoseconds apart. And she did so because she pressed the buttons at the same time. Bob argues that Alice must be mistaken, that if the first statement is true, then Alice must have triggered the eastmost light 6 nanoseconds earlier than the westmost light, as light cannot violate causality. When Bob has the lights, he reports that the lights reach him at the same time, 0 nanoseconds apart. And they did so because he pressed the buttons at the same time. Alice argues that Bob must be mistaken, that if that first statement is true, then Bob must have triggered the westmost light 6 nanoseconds earlier than the eastmost light, as light cannot violate causality. Alice and Bob both agree that the other's far light had to have been switched on first, but both say that they turned their lights on at the same time. One possibility is that the far hand experiences time differently than the close hand. Perhaps this is a brain effect. Maybe our right hands attempt to balance out neural length differences with a default 6 nanosecond delay. Unfortunately, this cannot be true, as the delay again shows up if we switch directions, and then it is the left hand that appears to experience that time delay. Still, maybe it is a brain effect, where the hand furthest from the forwardness is delayed for some reason. So Alice and Bob construct a new experiment. No hand switches to remove this possible bias. Instead, Alice and Bob fix clocks to their east and west walls. According to each investigator, they see their own clocks as ticking at the same time, reading the same time at the same pace. However, the other experimenter must disagree that their clocks are synced. Despite not being able to see the other person's results, as the light takes too long to reach them, they know that the light that traveled in the direction of motion must have come from an earlier time, according to them, as the light from the back end takes longer to reach the investigator in the center. So both investigators know that their clocks appear to read the same time simultaneously, but they must also know that since one or both of them is in motion, then the light moving in the same direction as their motion must have been emitted earlier than it would appear. And therefore, if they approached the clock on the back end, they would see it speed up as they move towards its proper time. So the clock in the front is actually behind, and the clock in the back is actually ahead, such that the difference in distance the light needs to travel to reach the investigators balances out to appear to arrive at the same time. This is because light travels through the quantum photon field, or ether, as opposed to being a type of object that experiences time and space. Light is not contained in the ship like the air and man and ball and flies and fish were. This clock setup is merely another example of the relativity of simultaneity. The lights coming from the flash bulbs or clocks were emitted or reflected at different locations at different times. A weirder effect occurs when the two investigators, within their own frame of reference, record the same time, but based on the travel distance of a mover, the other must calculate that the other's clock is moving further. So if they are recording 1 second, and you know it traveled more than 1 second amount, their clock must be slow. One of the thought experiments that demonstrates this is called the light clock, which is a perfect mirror box that has a trapped photon inside, such that the photon of light bounces up and down in the box, and each time the photon does a number of bounces, it counts out the seconds of a normal clock. As a simple example, 1 second may be counted when the photon does one complete trip from the top to the bottom and back to the top. In reality, such a clock would require millions of bounces to count 1 second, as light moves at 3 × 10⁸ meters per second. So if the box were half a meter tall, then one complete trip would be 1 meter, and so to count 1 second would require 300 million complete trips, or 600 million minus 1 bounces. I have a different clock that we can use. It's our neurons. A lot of your nerve cells have a long cord called an axon, and that axon is insulated with what is called a myelin sheath. The axon is long, such that a single cell can reach far across the body to communicate its signal, and the myelin sheath helps to make that signal move faster. Together, the signal of touch can move at 80 to 120 meters per second. As most people are between 1 and 2 meters, a 100 meter per second signal can travel up and down the average person 50 to 100 times in 1 second. For a signal to be felt, it does not need to travel all the way to the brain. Some signals can be felt at the moment the signal reaches the spine, such as the knee-jerk reaction or reflex. So imagine Bob is 2 meters tall. His legs are equal in length to his torso and head, making his legs 1 meter long. As Bob moves along inside the train, which is moving at 0.7 c, Bob feels a pebble in his shoe. If we were to set up a neurology lab in the train and hook Bob up to an EEG machine to test his nerve impulses, we see that Bob's signal moves at 100 meters per second, or 0.1 meters per millisecond. So it takes 10 milliseconds for the signal to move from the foot to the spine. If we repeat this neurology lab in the stationary frame, Bob's nerves still receive the signal after 10 milliseconds. So we can say that Bob's nerves are constant. They always receive the signal in the same period of time, 10 milliseconds to travel 1 meter. But Alice is not convinced. Alice never got on the train and never saw the lab being done, but she trusts her colleagues would not make such a mistake. But clearly something is wrong. For when Bob was on the train, the signal that started in his foot traveled straight up his leg to his spine in 10 milliseconds, but his spine was no longer 1 meter away. After the first millisecond, the spine, Bob, and train had moved 210,000 meters eastward. If Alice calculates how long according to her clock it should have taken the signal to travel, given the motion of Bob and his train, Alice must argue that by her clock, it would have had to take longer than 10 milliseconds. However, Bob counters and says that from his point of view, it was Alice who had the nerve signal that took longer than 10 milliseconds to be received. Given that he has the lab equipment using electrical signals that move at the speed of causality, he argues that it cannot be wrong that it took him 10 milliseconds, whether his frame is moving or not. And he argues that it was in fact Alice receiving nerve signals slowly, and therefore experiencing time slowly, and therefore seeing him slowly. If relative motion affected the speed of our nervous system, we would never move, as every time we started moving with a constant velocity that is different from the stationary Earth frame of reference, our nerves would fail to function properly and we would die. unable to signal the heart to beat and lungs to breathe. There is only one solution that solves the conflict. Velocity is relative, simultaneity is relative, and now we also know that time is relative. We already found the math that will help Alice find the time difference. According to Bob, his clock says 10 milliseconds, so she needs to write the equation delta t prime equals gamma times delta t. Delta t is Bob's time according to Bob, 10 milliseconds. And when Alice plugs that in, she finds that it actually took 14 milliseconds. Since Bob thinks he is stationary and therefore gets 10 milliseconds, Alice accounts for his motion, just like in Galilean relativity, and gets that Bob's clock is actually ticking slow relative to hers, not that his nerves are speeding up. Bob cannot witness this because Bob, his nervous system, his clocks, everything at that velocity is experiencing time differently from Alice. But according to Alice, Bob's clocks reach 10 milliseconds after what is really, in the Earth frame, 14 milliseconds. Since velocity is relative, and velocity is distance over time, and time is relative, we have to ask, is distance also relative? We can check if distance or length is relative. Distance is length between 2 points, typically associated with velocity and the time it takes to get places. But distance itself can be represented with a static map, such that the time of measuring distance on the map would make no difference. Two houses a mile apart remain a mile apart on the map, no matter how fast you move objects on the map, or what time of day you measure it. Therefore, if we want to know the length of an object, we can make it sit still, and measure its top, and then its bottom, at different times or days, but since it's not moving, that's okay. One of the issues with length in these cases is how do you measure a length when it's moving? For instance, when you have a map that shows two houses are 1 mile apart, it doesn't matter how fast you move toy cars on the map. The distance is the same. What if you move the map around very fast? Does the distance change now? As, by the time you have a chance to move your eyes to the other end of the ruler, the location changed, including the first end, which is no longer at the first house. We found that if an object is in motion, then the two frames of reference will argue over whether or not their clocks were synchronized or not, and this causes an issue in the agreement of length measurement. So if we want to measure length, human clocks and rods will not be very useful to us. Instead, we can use the properties of light to get what we want. Light always travels at the same speed, so we don't have to worry about whether the velocity is relative. Given that, Alice and Bob set up a new experiment. Alice and Bob fix a laser pointer at the back of their trains, and a mirror at the front ends. The laser is fired across the train length, hits the mirror, and returns back to the source at the back wall. The length of the train is therefore the distance the light traveled, and the time it takes to travel is the distance divided by how fast it traveled it. So for Alice, who is stationary on the Earth at the train station, the light traverses the inside of her train without the train itself moving, and so the distance the light needs to travel is the train's length twice, and its change in time can be found by dividing the twice train length by the speed of light c. Bob disagrees because to him Alice is in motion, and Bob states that to him he is motionless, and her calculations are actually his, that it took his photons twice the length of the train divided by c. But Alice knows that it is Bob that is in motion, and so Alice does the math to check what is happening here. According to Alice, when Bob's train's back end lines up with hers, it fires a photon towards the front of the train. But the train is moving in the same direction of that photon. So the photon approaching the front of the train must travel the distance of the whole train, plus the distance the train moved in that time period. Once the photon hits the mirror and starts to return to the back of the train, the distance it would have had to travel would be the length of the train. However, before it can do so, the back of the train races up to meet the light, and so the second photon travels the length of the train minus the distance the train moved in that time period. She finds that the change in time of the moving train must be gamma squared times the stationary frame of L2 over c. If Alice used the relativity equation of change in time of one frame of reference for another, and she plugs in the equations her and Bob found, then Alice comes to find that the length of a moving train is less than the length of a stationary train. When we get Bob moving at 0.866 c, Bob and his train reduce in length by a half. Bob's 2-meter-long train is now 1 meter in length as he moves. Of course, to Bob, he is normal, he is not moving, and Alice is the one that appears to be reduced in length, in the direction of her motion, by half. Einstein's discovery that the Galilean principle of relativity had a special case, due to the nature of light, demonstrated that the principle of relativity said more than just velocity is relative, and showed that it also proves that simultaneity is relative, time is relative, and distance and length are relative. Therefore, Einstein used this discovery to show that Maxwell's electrodynamics does not have a relativity problem, just a Galilean relativity problem. By involving a simple parameter, gamma, Galilean relativity becomes more powerful, and can now deal with objects moving near the speed of light. Einstein showed then that the charged particle, from its point of view, is stationary. However, the wire which appears to be moving is reduced in length, and therefore has more positive charges closer together, and therefore the wire appears to have an electric field, which interacts with the electric field of the positively charged particle, and therefore is repelled away from the wire. This solved the Maxwell-Galilean relativity problem. Just like with the Galilean principle of relativity, if you assume it to be false, then you would have to accept that every event involving velocity would have 2 or more causal realities, such that to one group of people, the ball was thrown backwards, and to another group of people, the ball was thrown forward. Likewise, if you assume the special theory of relativity is false, then you must accept that 2 or more causal realities split from the event every time an object or photon moves. Without requiring the assumptions of many worlds, special relativity answers the question of what time and length mean to moving objects, and does so without violating causality. Since causality is the one big thing we really cannot violate, then the special theory of relativity must be accepted as true. The alternative is to violate causality or to form many worlds for each and every velocity. Let us leave off with a real-life example. The sun sends out high-energy particles that move through space at near the speed of light, and upon hitting the Earth become a bunch of secondary particles, one of which is called a muon. The muon is an unstable subatomic particle, which has a mean lifetime of 2.2 microseconds. Given the short lifespan of a muon, under regular Galilean relativity, the muon would decay before it can reach the ground. However, muons reach the ground all the time. Given the distance they have to travel from creation to annihilation, from the atmosphere to the ground, the speed and lifetime of the particle is too small to survive all the way to the ground. Calculations show that it would take 6.4 microseconds at its speed to reach the ground. So how are they doing it all the time? Well, the muon is traveling at 0.99 c. So from the ground, we would see that the muon's clock is slow and is ticking to 2.2 microseconds in what to us is actually about 10 microseconds. And to the muon, it appears that the distance between the atmosphere and the ground has reduced from 2,000 meters high to 280 meters high, so it can reach the ground in 2.2 microseconds. If time dilation and length contraction were not facts about the nature of motion, then nearly all of the muons would decay in the upper atmosphere, which is not something we experience. Let us review our list of principles. Existence exists. A is A. Consciousness is conscious. The universe is causal. The universe is full. nothing is prior to the little stuff. The Galilean principle of relativity is valid. Light is an electromagnetic energy disturbance in the electromagnetic or photon field, which always travels at a constant velocity in the ether because of the properties of the ether. The special principle of relativity is valid. Einstein, in his third paper of 1905, showed that there was a causality problem between Maxwell's electrodynamics and Galilean relativity, and that the only true issue was that Galilean relativity was unable to measure the speed of light, and therefore unable to see that as objects increase in velocity towards the speed of light, that a factor needs to be introduced to keep the speed of light constant. It was, however, Einstein's fourth paper of 1905 that brings us here today, and brings us into the theory of general relativity. After Einstein introduced special relativity by finding a problem between Maxwell and Galileo, he kind of repeats this process by attacking himself and his special principle of relativity, as there must be an effect on the principle of the conservation of energy, which might not be good. His fourth paper is very short, containing in the English translation only 717 words. As such, allow me to translate the English translation into something a little more digestible. The results of the previous investigation lead to a very interesting conclusion, which is here to be deduced. I based that investigation on the Maxwell-Hertz equations for empty space, together with the Maxwellian expressions for the electromagnetic energy of space, and, in addition, the principle of relativity. With these principles as my basis, I deduced the following results. Let there be a system of plane waves of light possessing the energy L in the system of coordinates S. If we introduce a new system of coordinates, S', moving in uniform parallel motion with respect to the system S, then, according to the system S', this quantity of light possesses the energy L times a relativistic shift. Let there be a stationary body in the system S, and let its energy, in the system S, be called E0. Let the energy of the body relative to the system S', moving as above with the velocity v, be called H0. Let this body, which remains at rest with respect to the system S, send out plane waves of light, of energy 1/2 L measured relatively to S in equal and opposite directions. The principle of energy conservation must apply to this process with respect to both systems of coordinates by the principle of relativity. If we call the energy of the body after the emission of light E1 or H1 respectively, measured relatively to the system S or S' respectively, then by employing the relation given above, we obtain that the energy of the stationary body at the start is equal to the energy of the stationary body after, plus 2 released packets of energy, which together have the energy L. Whereas from the S' moving frame, we measure that the original energy of the body, before sending out plane waves of light, is now equal to the energy of the body after, plus the energy of L with a relativistic adjustment. By subtraction, we obtain from these equations that the difference in the initial energies minus the final energies equals the original energy of the plane waves times gamma minus 1. The two differences of the form h minus e occurring in this expression have simple physical significations. H and E are energy values of the same body from two different systems of coordinates, which are in motion relative to each other, the body being at rest in one of the two systems, in system S. Thus it is clear that the difference h minus E can differ from the kinetic energy K of the body with respect to the other system S prime with the addition of a constant. The kinetic energy of the body with respect to S prime diminishes as a result of the emission of light, and the total decrease is independent of the properties of the body. Moreover, the difference K0 minus K1, the kinetic energy, depends on the velocity. From this equation, it directly follows that if a body gives off the energy L in the form of radiation, its mass diminishes by L over c squared. The fact that the energy withdrawn from the body becomes energy of radiation evidently makes no difference. So we are led to a more general conclusion that the mass of a body is a measure of its energy content, where L is a measure of energy. M equals E over c squared, or E equals mc squared. If the theory corresponds to the facts, radiation conveys inertia between the emitting and absorbing bodies. And with that final line, Einstein ties up all four of his 1905 papers. Having started by demonstrating Brownian motion is best explained by the existence of atoms, and then that light is a form of radiation energy which exists as quanta and can provide enough energy in a single hit when tuned properly in order to break the bonds between some metal, i.e. an atomic structure, and one of its electrons. He then proved that the motion of photons and electrons and other quantum particles are too fast for Galilean relativity to get accurate, and you need to account for that speed in terms of not just velocity, but of its components, length and time. And finally, that because of this fact of special relativity, it must also be the case that mass and energy are equivalent, and that in fact, the Brownian motion of paper 1 is caused by the fact that atoms exist as quantum particles who exchange energy through radiation, i.e. photons, and that photons are in fact a kind of massless mass-energy converter which conveys inertia between the emitting atoms and the absorbing atoms, thus moving them around. This also means that if you add energy to an object, say increase its temperature or force it near an object it is electrically repulsed from, then it will increase in mass. It also means, though, that if an object in motion perceives energy that is emitted from a body, it will perceive it with a relativistic shift. The kinetic energy of the object appears to be changed, and the laws of conservation of energy cannot allow for a loss or gain in energy without a counterbalance. Einstein thought about this for 2 years. Let us be Einstein ourselves and work this out. 1. Everywhere we go, the laws of physics are the same, even when we are in motion. 2. The speed of light is always constant. 3. Velocity is relative, and the faster our velocity, the bigger the difference in appearance of our length and time will be to others not moving along with us. 4. The faster our velocity, the bigger the apparent difference of kinetic energy, and therefore the bigger the apparent difference of mass to an observer who is not in our frame of reference. 5. Typically, when we think about mass, we think about heaviness and falling down. Given that falling is a form of motion and is related to mass, then falling is related to energy, which we also already know as that is the difference between potential and kinetic energy of massive objects. Therefore, there must be a relativistic effect here as well. 6. However, relativity has only really dealt with constant velocities. But we know from Galileo that all objects accelerate, that is, positively change velocities over time downward. And, more so, that all objects accelerate down to the Earth at the same rate. 7. It thus can also be the case that the principle of relativity applies in some fashion to accelerated reference systems. Think about it like this. Again paraphrasing Einstein, what if a gravitational field is like an electric field, which is generated by a magnetoelectric induction? What if the field only exists because of some relativistic effect? In such a field, where you are a charged particle and the electric field becomes more attractive the closer you get, you therefore accelerate towards it. What if gravity were as such? For example, if I placed you in empty space, meaning far from any other objects for millions of astronomical units, with a strong magnet in your pocket, then, somewhere in the distance, I place either a massive body or a super large magnet in the opposite polarity of yours. Before you know what the object is, you see me place something. And you see the moment that I do, that you slowly, at first, start moving towards me and the object. And over time, you start moving towards it faster and faster. Without seeing it, how would you know if you are falling towards a massive body through gravity or accelerating towards a magnet? Before we get Einstein's answer to this question, let's start back at the beginning. We have gotten so tied up with light in the supposed vacuum of space that we lost track of rocks and planets and the nature of things falling down or up back to their natural places. Let us fall back to 500 BC. Heraclitus told us that Logos keeps the cosmos in harmony, moving all objects by a kind of law, by a sort of reason. This philosophically divided the world into two halves. To some, Logos is logic and natural law, and to others, Logos is logic and consciousness. This makes sense, as in order for us conscious beings to recognize facts of reality, and therefore form rules of logic to help us further identify other facts of reality, we necessarily have to have a consciousness capable of discovering facts, and thinking, and reasoning, etc. So, depending on your metaphysical basis of reality, e.g., a belief in a god or gods or scientific reasoning of Big Bang cosmology, will shape how you view the logos of the cosmos. Is it divine reason held in place with natural laws? Or is it natural, to which we have reasoned out some laws that aid our understanding? Aristotle was under the belief that logos was here on earth, as compared to his teacher Plato, that put logos in a divine creature that saw a cosmos of disorder and decided to organize it. Aristotle, given his observations of the nature of reality on earth, found that all objects of their own kind tended to find their way to their place in the order of all things, and that in order to move something required a constant force. This then was the first philosophical theory of gravity and inertia, that it was causal by the nature of the objects. Due to the fact that Aristotle was not aware of the concept of friction, this caused him, as it does to most people, to conclude that an object at rest remains at rest until you add a force to it, and that an object in motion will come to rest without a force constantly acting on it. Or otherwise stated, an object in motion will only remain in motion while a force is applied to it. This led Aristotle to hold that objects will fall at different rates because of their mass, type, and the medium in which they are falling. Following Aristotle was the Christian theology and the Dark Ages they brought upon humanity for over a millennia, where the Logos became a humanoid figure with a plan to save humanity from the pain he's inflicting on them. On our first run through this timeline, we were focused on the stars in the celestial sphere as we passed from Aristotle to the Church, making those spheres levels of heaven, and the later shift in perspective that Earth was not at the center of those celestial spheres. However, this time we are exclusively focused on gravity, mass, and inertia. So we are going to take a detour to the Islamic world around the year 1000. Here we meet a prominent figure in philosophy and science, and whose accomplishments are typically passed off as being some European's accomplishment. The hero of this era goes by the name Ibn, or as he is known by the Latin corruption of his name, Avicenna. Ibn, in his philosophical encyclopedia, The Book of Healing, which is not a medical text, but rather a metaphorical healing of the soul through scientific experimentation and examination, provided us the philosophical thought experiment that Descartes would later utilize and get full credit for. Ibn, and 600 years later Descartes, constructs a thought experiment called the floating man. He speculated on what a man detached from objects of perception would be like. He's floating, without air pushing him or pressing against him. He cannot see or taste or touch or smell or hear anything. Can the man be self-aware of his existence in this floating space? Despite this topic historically swerving into ontology, epistemology, and psychology, this exact thought experiment will show up again with Einstein in 900 years. Both Ibn and Descartes conclude, quite illogically, that the man must be self-aware. He, according to them, thinks, and therefore he is, and he does so because God. Well, that will not be much use to us at the moment, but we will stick a pin in this floating man thought experiment and use it for something else later. What was most important from Ibn at this time, however, was the conclusion he made about motion, which again Descartes would take 600 years later, but would not get the credit as Newton scooped it from Descartes in a like fashion. Ibn disagreed with Aristotle, and rightfully so, and distinguished the difference between an object moving due to its inclination to its natural state, and a force applied to an object, and that the inclination of motion on an object is in fact imparted to it by a force. That an object thrown by a man will have its energy of motion come from the logos of the man throwing it, and that the object will continue to move at that constant velocity forever or until acted upon by another force in the opposite direction. Essentially, inventing the conservation of momentum laws and the Newtonian laws of motion in the year 1000. Jump 500 years forward, and Copernicus is flipping the heavens around and changing how we view our place in the universe, which necessarily means questioning why things fall down, if the center of the Earth system is actually the Sun in the center of a solar system. If Earth is essentially in the celestial sphere of the Sun, which we can now call the planetary orbit, then why do rocks fall down if Earth is not at the center? Now, somehow, it is the rock that moves around the stationary fireball. We can, for the most part, just agree with Aristotle still, and say, well, fire goes up to naturally exist with the sun, and the rocks fall down to be with the earth. But in order to do that, we'd have to ignore Ibn. That's fine, said the church. We will pretend he doesn't exist. In 1609, Kepler published his book called A New Astronomy, which includes the first two laws of planetary motion and states that the true theory of gravity rests upon the following axioms. Every corporeal substance, to the extent that it is corporeal, has been so made as to be suited to rest in every place in which it is put by itself, outside the orb of power of a kindred body. Gravity is a mutual corporeal disposition among kindred bodies to unite or join together Thus, the earth attracts a stone much more than a stone seeks the earth. The magnetic faculty belongs to this order of things. Heavy bodies, most of all if we establish the earth in the center of the world, are not drawn towards the center of the world because it is the center of the world, but because it is the center of a kindred spherical body, namely the earth. Consequently, wherever the earth be established, or whithersoever it be carried by its animate faculty, heavy bodies are drawn to it. If two stones were set near one another in some place in the world outside the sphere of influence of a third kindred body, these stones, like two magnetic bodies, would come together in an intermediate place, each approaching the other by an interval proportional to the bulk of the other. Galileo tested experimentally the effects of this gravity by rolling balls down ramps. Galileo got a very small inclined ramp. The small incline meant that the ball was not going to be as affected by air resistance, which becomes more apparent the steeper the drop. Likewise, Galileo knew that if you dropped a ball from a short height from the ground, the impact the ball would make with the ground would be small, as compared to when you drop the ball from a high height. The higher the ball, up into a point, the harder it hits the ground, and therefore, something is happening here. Galileo did not have clocks, or cameras, or lasers, etc. So in order for Galileo to measure the rate of the balls as they rolled down the ramps, Galileo used water leaking at an equal rate from a vessel, and then measuring the weights of the water that was released in the amount of time the balls were rolling. Galileo found that the amount of weight in the cups was changing between certain intervals. For example, when he starts the ball at the very top, compared to starting at halfway, the water weight difference is not half as you might expect. In fact, it would take about an equal amount of time for the ball to go down a quarter of the ramp as it would for it to go down the remaining 3/4. And likewise, if you start at the middle of the ramp, it takes about the same time to move a quarter of the way from half as it does from the other 3/4 of that half. It appears as if, in fact, there was a mathematical pattern to the motion, such that we can say that the distance it covers increases over time, aka it is speeding up. It is changing velocity over time. Galileo calculated that distance is equal to the square of the time, such that after 1 unit of time, the distance was 1 unit of length. After 2 units of time, the distance was 4 units. After 3 units, 9 units of distance, etc. Galileo was thus able to place a bell at a distance of 1, 4, 9, and 16 units from the starting point, and as the ball traveled the distance with acceleration, the bells each play at the same tempo. Galileo continued to drop balls of various weights and sizes down various ramps until he proved that 1. Distance is proportional to the square of time for everything, and 2. That objects retain their velocity in the absence of any impediments to their motion, i.e., has inertia. Galileo wrote, "Imagine any particle projected along a horizontal plane without friction. Then we know that this particle will move along this same plane with a motion which is uniform and perpetual, provided the plane has no limits." Some 40 years later, Robert Hooke told Newton about his hypothesis of orbital mechanics and the inverse square law of planetary motion. However, Hooke refused to show his proof and did not publish those results. But Newton did publish his mathematically derived mechanics of Kepler's laws of planetary motion, and then published the hypothesis of the inverse square law of universal gravity, making an enemy with Hooke that lasted the rest of Hooke's life. Newton's publication read, "I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve, and thereby compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the earth, and have found them to answer pretty nearly." End quote. The force of gravity is proportional to the mass of object 1 times the mass of object 2 divided by the distance from their centers squared. This is the universal law of gravitation, and it states that every particle attracts every other particle in the universe with a force that is proportional to the particles' masses and the distance between their centers of mass. This formula cannot, however, be used as an accurate equation until we find the gravitational constant, that rate of gravity which is true everywhere. G is the constant of proportionality attracting any two bodies from anywhere in the universe. The tension in the ether, if you will, the spring tensions of the ether of Hooke's, or the tension in the lines of force of Faraday, who historically here is yet to come. It was this confusing little constant of proportionality that made people skeptical of Newton, for he is essentially stating that there is an atom on a planet in the star system of Proxima Centauri which is attracted to an atom in you. In fact, to every atom in you. By what means was there to suppose this action at a distance, his colleagues scoffed. Newton, however, didn't really care about that, because he didn't need to postulate a hypothetical ether in order to account for his ideas. He had math, and the math worked every time. Well, not every time, but we will get back to that later. We needed to find this gravitational constant to make the calculations really accurate. Knowing the approximate mass of the sun and planets, and their distance between each other, provided great measures without the constant. But to predict things to the degree, to a second, would require more precision, and the fact of the matter is that not having a constant will always lead to failure. The constant must exist. Enter Henry Cavendish, who found a way to measure the gravitational constant. An elaborate setup which was a type of replica to Coulomb's torsion balance experiment. As the formulas are identical, so too is the experimental setup, kind of. A torsion balance holding two 350-pound lead balls, suspended opposite from each other, which had two smaller 2-pound balls positioned around the larger balls. The smaller ball's attraction with the larger ball was the main focus of the experiment. The use of two each is to balance on the torsion wire. As the smaller balls and larger balls mutually attract one another, this puts tension on the suspension string, which causes the suspension string to twist. The structure eventually comes to an equilibrium, where the torque on the wire can provide a measurable value of gravitational attraction. Cavendish's results were not as accurate as we have today, but compared to everyone else in 1797, he was the closest. And he found that the force on the wire was 1.74 times 10 to the negative 7 newtons, and therefore accounting for the masses of the balls and the distance between them, Cavendish found the value of G to be 6.74 times 10 to the negative 11 meters cubed per kilogram second squared. Today, we know that that value is 6.67408 times 10 to the negative 11 meters cubed per kilogram second squared. Two of the mathematical calculations of planetary motion did not work even after Cavendish found the universal constant G, and those were the orbits of Uranus and Mercury. In 1843, John Couch Adams and Urbain Jean-Joseph Leverrier independently predicted that there must be another planet, as the discrepancies between Kepler's laws and observations of Uranus were not making any sense. Unless something else was pulling on Uranus from outside the system. Given the orbital mechanics of Newton, if you assume another body must exist, and it does, then you will be able to predict when it is going to pass near other objects. By 1846, the planet Neptune had been discovered, when Leverrier sent his colleague the position in the sky to look, and that colleague, Godfrey Gale, found the planet right where Leverrier said it would be. Mercury was then the only object that Newton's laws could not fully account for. So many speculated another planet closer to the sun, and they chose the name Vulcan, for the Roman god that forged the weapons of the other gods in his furnace under the island of Volcano. This brings us right back to Lorentz and Einstein. So we return to Einstein in 1907. In 1907, Einstein assumes, quote, the complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system, end quote. And, by doing so, also predicts that clocks dilate due to gravity, and that light should bend in the presence of a gravitational field. He did so by extending the principle of relativity to an object with a constant acceleration. A constant acceleration means that the velocity changes over time. If you imagine a frame of reference which is moving with the object, both of which are moving relative to the stationary frame of reference, we could imagine putting a velocity frame of reference at the location of the accelerated frame for each unit of time. If we restrict ourselves to the small changes in the beginning and set them all together at t equals 0, then after the first click, the s' frame and the sigma frame are now in location 2 together. If we synchronize our clocks in the s' frame, we know by special relativity that for this to be perceived as true for people on s', then people on s will calculate the front clock as being behind in time and the back clock as being ahead in time. After the next unit of time, sigma no longer matches s' or s. When the s' and s' frame calculate the difference of sigma's local time from their perspectives, they find that the local time of the object is equal to the total of the other two times, call it tau, times 1 plus the acceleration over c squared, times the distance from the observer. However, from the point of view of a single object that spans that length and exists in the frame of sigma, it is required to use the time tau, which appears as a normal functional clock to them. Einstein, having already assumed that we cannot tell the difference between being in an accelerating frame of reference and gravity, shows that we can replace the acceleration of the frame and the distance with phi, the gravitational potential, obtaining that clocks above the ground run faster than the clocks on the ground by a factor of 1 plus phi over c squared. Given this, Einstein then proceeds to show that that fact will have an effect on photons, that gravity will affect photons despite photons having no mass. Einstein showed that momentum is replaced by momentum times this factor, and likewise the speed of light is replaced by the speed of light times this factor. Therefore, Einstein was able to show that light rays that propagate with the x-axis are affected by the gravitational field, and that the light rays which do not propagate along the x-axis are bent by the gravitational field. It is important to note here that this does not mean that the speed of light actually changed, but rather that the accelerating frame's spatial coordinates are changing in a curved manner. The coordinate velocity of light changes, not the speed of light itself, which would be strange given that we need that number to calculate the appearance. This has a very important meaning in regard to Einstein's 1905 discovery that mass and energy are related, and that an object in motion appears to change in kinetic energy. More so, this discovery that even photons will be affected by a gravitational field helps illuminate the answers he was searching for. Einstein had previously stated that if you add energy to the object, for example, forcing a magnet near another magnet that it is repulsed from, that gain of energy will increase its mass. Einstein was now looking to show that if that object is a mass and the energy you add to it is caused by gravity, that the result will be the same. Given all of the above conclusions of special relativity, Einstein concludes the paper stating, quote, "This equation expresses the principle of conservation of energy and contains a very remarkable result. To each energy E in the gravitational field, there corresponds an energy of position that equals the potential energy of a ponderable mass of magnitude E over c squared. Thus the proposition that to an amount of energy E there corresponds a mass of magnitude E over c squared holds not only for inertial, but also for gravitational mass." End quote. In 1911, in the paper titled On the Influence of Gravitation on the Propagation of Light, Einstein expanded the views he established in 1907, including postulating in the introduction of that paper that one can test his hypothesis by looking for rays of light passing near the sun, and you will find that they are deflected by about 1 second of arc. In this 1911 paper, Einstein shows that the gain of inertia mass from a gain of energy is identical to the gain of gravitational mass from a gain of energy, and that it is in fact the principle of relativity that merges the principle of conservation of mass into the principle of the conservation of energy. Given this, he states that if you send radiation energy from a high position above the ground down to the ground, and assume there is no gravity, but you find a way to accelerate the object to the ground, then, given the special relative nature of clocks and lengths, the energy that the ground receives will be greater than the energy sent. And by that same argument, the speed of light, c, at ground, should appear to be equal to the speed of light on the ground plus the speed of light at a given gravitational potential phi divided by c squared. And, therefore, he writes, quote, "The principle of the constancy of the velocity of light does not hold good in this theory in the formulation in which it is normally used as the basis of the ordinary theory of relativity. That the velocity of light in a gravitational field is a function of place. That light rays propagated across a gravitational field must undergo deflection." Einstein then states how we must model this by returning to a plot where light is constant, and through Huygens' principles of light, we deflect a plane of light by using circles and taking the flat spacetime, and we get the angle of deflection. Einstein then concludes that, quote, "A ray of light traveling past a celestial body undergoes a deflection in the direction of decreasing gravitational potential, and thus in the direction towards the celestial body." Everyone wanted to prove this was either true or false, and given that they had stars and a sun nearby, it seemed pretty simple. First, we just need a solar eclipse, so that the sun does not blind us when we look near it. Then we just need to measure where the stars behind the sun are. Then we wait for the sun to move from in front of those fixed stars, and check again in 3 months to see if the relative distance between them changed when there is a massive object between them and us. Well, it was not that easy, because if you do any astronomy, you know that clouds will ruin everything. In October 1912, during the first solar eclipse available, it rained. So they tried again August 21st, 1914, and again, clouds. Then, and you'll know why if you are a bit of a history buff, you'll notice that the next few years of science into the angle of deflection of light caused by massive celestial bodies stopped in order to start working on science for projectile weapons and flying machines and big heavy armored vehicles. In 1916, Einstein proposed 3 tests for general relativity, which subsequently became called the classical tests. The first was that the general theory of relativity properly calculates the precession of Mercury's orbit, predicting an extra 43 seconds of arc in its precession. Second, light will be deflected by the sun. Third, that light escaping from a star or planet will be redshifted, meaning its wavelength will appear more in the red section of the visual light spectrum. It was already established by 1882 that the measured precession of Mercury was approximately 43 seconds of arc. In May 1919, Arthur Stanley Eddington was able to prove Einstein's second test for general relativity, finding the light from stars of Taurus from behind the sun that had deflected at the angle that Einstein had predicted. Finally, in 1925, results for measuring the star Sirius proved to have been redshifted. In 1959, the Pound-Rebka experiment proved Einstein's gravitational time dilation here on Earth. Einstein's theory of general relativity was also able to predict the cosmological constant universal expansion, the Big Bang, the cosmic microwave background, black holes, and gravity waves, all of which have been demonstrated beyond a reasonable doubt today. Thanks to these discoveries, global positioning satellites are able to keep proper time on Earth by adjusting their on-board atomic clocks with a special and a general relativistic shift to counteract the velocity and gravitational potential of the satellite and its clocks. If it were not for Einstein's general theory of relativity, any satellite we threw up into space with a clock on it would very quickly become out of sync with our clocks on the ground, and our GPS would tell us to drive into the ocean. If that which Einstein's general theory of relativity predicts does not actually exist, then the global positioning satellites above Earth would have no reason to time dilate. Putting it all together. From Earth, without ever leaving the planet, it appears that the Earth is flat, and when you walk all the way around it, your feet never leave the ground and start walking on the ceiling for half of the trip. So it appears to you to be horizontally in front of you forever. But if you leave the planet and go hang out on the moon for a while, and you watch your friend walk around the planet, you see him walking around a ball, like a bug on a basketball. Likewise, up close, i.e., locally, all experiments of light are in a flat spacetime, and it's at its universal constant velocity, moving in a straight line. If you get a global picture, however, things start to become a little more complex. Given that we are doing our experiments on Earth in relatively tiny observatories, we cannot see the curve, just the final results, which appears to us as to have arrived in straight lines. Mathematically, then, we need to include a thing which prevents us from forgetting that the universe is not entirely flat, which will keep our lengths accurate to reality. The mathematics required to move between flat and curved spacetime are tensors, which is not something we are going to get into. All that needs to be said here is that a new metric was formulated which captures all of the geometric and causal structures of the space-time ether, meaning that it can be used to define notions of time, space, distance, volume, curvature, angle, and temporal separation. Einstein required using this new form of mathematics in order to better describe the universe. Starting then from the very beginning, if you are a mass, then that means you are composed of atoms or pure energy. We are made of atoms. Atoms are just regions of the ether which are stable and bound tightly in a tiny space which cannot be occupied by different energies of the same kind, in the same time and in the same respect. The stability of the atom is caused by atomic forces which interact and change, and this means everything with mass also has frequency, and therefore is also a clock. All masses are thus their own type of clock, which always interact at the speed of causality. The speed of the ether interacting with itself is what allows for that stability of the atom, of that mass, of that clock. Now your atoms send that energy around through the use of photons. Photons always travel at a constant velocity c, in vacuum. If an atom in your foot shoots out a photon that is absorbed by an atom in your head, and you are in a box, and that box is said to be motionless, as you are not moving while it is on the surface of Earth, then you know that the length the photon traveled was your height. And given your height and the constant velocity of light, you can calculate the time duration. If, however, your box is in empty space, moving upward at a constant velocity near the speed of light, then the photon from your foot atom will still be traveling at a constant velocity c, and will still pass you by at c. If you think about how this could be, it is only possible if the photon from your foot was traveling for a longer amount of distance, the distance to the original place of your head, plus the distance moved at the box's velocity. And if the clocks of your foot atom and your head atom are synchronized, such that to an atom in your torso, it receives the photons of the foot and head at the same time, meaning that the foot photon clock is ahead of schedule, and the head clock is behind schedule, such that the longer distance of the foot photon matches the clock of the shorter distance of the head photon. The torso runs into the head and runs away from the foot. Thus, to be seen at the same time requires different set times. If, however, your box is an empty space moving upward at a constant acceleration, acceleration is an absolute state of motion, and everyone inside and outside of the accelerating frame knows which frame is accelerating and by how much. For example, if you have 4 boxes moving in space, one is with us. We are considering a stationary rest frame. 2 are moving at a constant velocity, one moving from below us to above us, the other moving from our right to our left, and one is accelerating. The effect of relativity is that we cannot tell the difference between a motionless frame, like ours, and a moving at a constant velocity frame, like boxes 2 and 3. And so, when we see our accelerometer, it is a box with a ball in the middle, held in place by springs. When we look at the accelerometers of one of the other velocity frames, those balls are also in the middle of their boxes, despite us seeing them moving and expecting a little tension on the springs in the motion of that direction. Comparatively, when we look at the frame that is accelerating, we all see, including the people in that frame, that the accelerometer is stretching the spring at the top and compressing the spring at the bottom, and curving the springs at the sides. That is the sign of acceleration. And using Hooke's spring equation, we can calculate the force applied to the springs by measuring their new lengths. From all perspectives, then, we know that if you are accelerating upwards in your box when your foot photon sends its signal up to your head, then your foot atom, which has a mass, would lose energy, as we had seen in Einstein's last 1905 paper. By those same acceleration and special relativity ideas, the photon itself loses energy as it races to catch up with your head. After each second of the atom's clock, we imagine a new velocity frame of reference, which is changed drastically by the next time unit. But as photons cannot lose velocity, the loss of energy is within the photon's wavelength. And the wavelength stretches into the red part of the visible light spectrum, which is why we call it redshift. So long as you are in a uniform field of acceleration, the photons from your foot are going to lose energy when they reach your head, if it has the energy left to be seen. And as Einstein showed in the photoelectric effect, a photon with the wrong quanta of energy cannot excite the atom of the receiver. In the reverse manner, the atom in your foot would be receiving the photon with more energy, and the clock is moving much faster than theirs. This is different from constant velocity frames, where each observer sees the other experiencing the same phenomenon. E.g., in the constant velocity setup, if Alice sees Bob's clock as slow, then Bob sees Alice's clock as slow. But here in the accelerating frames, if Alice sees Bob's clock as slow, then Bob sees Alice's clock as fast. We can detect acceleration. Finally, if we cannot tell the difference between a uniform constant acceleration field frame and a uniform gravitational field frame, then special relativity holds for both. And therefore, a uniform gravitational field is equivalent to a uniform constant acceleration field. We know, however, that the gravitational field of Earth is not itself an accelerating frame of reference. For, say if the Earth were flat and accelerating upward at 9.8 meters per second squared, it would only take a relatively short time for the Earth to surpass the speed of light and continue accelerating past the speed of light, in which case nothing in the universe could ever causally interact, in which case we could not be having this conversation. Therefore, we are in a gravitational field, not an accelerating frame. And therefore, clocks on the ground of Earth tick slower than clocks at the top of a skyscraper. The equivalent principle therefore now states that a frame of reference experiencing a non-rotating freefall occupying a small region of spacetime, the laws of physics are those of the special theory of relativity. We can add to our list of principles, then, that the equivalence principle is valid. Finally, we must account for one last thing. The fact that we do not live in a uniform gravitational field in a global sense. Just from large scales, it is clear that to the people in America versus the people in Australia, up and down are, relatively speaking, in opposite directions. And this is true too for people in Ecuador versus people in Indonesia, which are not the exact same ups and downs as they were for the last two. The Earth is a sphere, kinda, so the downward field lines point radially inwards, and the acceleration you experience on the ground is coming from the ground pressing up against you. Mass is a kind of energy. Regardless of its size, a mass is composed of energy stuff, which can release and absorb energy. The fact that the universe is not entirely dark, the fact that there are stars, is proof that the plain light waves of energy from billions of stars are passing by you at every moment. And so it is safe to assume that if you can see that starlight, that your atoms, your mass, can absorb starlight, and therefore you were struck by a tiny amount of that star's mass, which is converted into momentum, which would cause your atoms to recoil a bit when receiving them. Therefore, you experienced a force. Therefore, you experienced a moment of acceleration. So two masses floating near each other in empty space will be experiencing tiny accelerations from photon momentum, and therefore also re-release that energy with tiny acceleration. Therefore, clocks closer to them tick slower than clocks further away. So everything with mass also has its own gravity, which we can express as meaning anything with mass interacts with the ether in such a way that time dilation bubbles around it. If you were to draw this as a Cartesian coordinate system, accounting for special relativity, you would create a world-line space-time diagram. And the fact that these mass time dilation bubbles exist maps onto the graph by making the appearance of curving lines, either in the motion of the accelerating object or in the fabric of the graph itself, combining together the fact of the gravitational time dilation bubbles around masses with a conceptual framework which is currently available to our 2 to 3 dimensional graphing language. One can show for a fact that gravity, the falling downness, is not itself a force, as it is identical to not experiencing a force at all in empty space. Anything that is equivalent to floating in space with not a single object or force field around it for billions of miles can be said to be caused by force. So falling down, the effect of gravity, is not a force. All we currently have, conceptually speaking, is analogous to curvature, to the markings of a line on a space-time diagram. And therefore objects which naturally move at constant velocities experience a change in time when they pass by a time dilation bubble. And due to the consequence of special relativity, the object never experiences a change in time, but rather, that change is expressed as a change in space, and the object falls down. Therefore, for all intents and purposes, we conclude that gravity should be considered, in the conventional sense, the manifestation of a curvature of the space-time ether, which itself is induced due to the presence of matter. This is the central tenet of the general principle of relativity, and so too will we add it to our list of principles, that the general theory of relativity is valid. Unfortunately, well, maybe fortunately, I think we're all having fun here, we're not quite done. Well, we are done for this video, but there is another aspect to this history that is very important for both the flushing out of the ideas that support these relativity videos, but also important for the future of physics. We need to talk about the history of quantum. Next time. Bye.